Chocolate is one of the world's most beloved indulgences, but behind every golden wrapper or glossy bar lies a story of craftsmanship and advanced engineering. From Toblerone's iconic peaks to Ferrero Rocher's golden spheres and Lindt's velvety truffles, each brand uses unique processes that transform simple cocoa beans into world-famous treats enjoyed across the globe. The production of Toblerone begins with the sourcing and preparation of its raw ingredients. The main base is Swiss milk chocolate, which itself is composed of cocoa beans, sugar, milk powder, cocoa butter, and a small amount of emulsifier to control texture and stability. Cocoa beans are harvested in equatorial regions such as West Africa, Central and South America, and parts of Asia. These beans are fermented, dried, shipped, and roasted before they ever arrive at the Toblerone factory. Once in Switzerland, the beans are roasted in large rotating drum roasters that allow precise control over temperature and time, coaxing out the flavor precursors that give chocolate its complexity. After roasting, the beans are cracked and winnowed in specialized machines that separate the outer husk from the valuable nib. These nibs are then ground in heavy-duty industrial mills until they form a thick liquid mass known as cocoa liquor. From this base, two critical components can be separated under pressure: cocoa butter, which provides smoothness and melt, and cocoa solids, which supply chocolate's intense flavor and color. Both of these fractions will later be recombined in the desired ratio. The sugar used in Toblerone typically comes from sugar beet grown across Europe or sugarcane imported from other regions. The sugar is refined to an ultra-fine powder because chocolate manufacturing requires extremely small particle sizes to create a smooth, melt-in-the-mouth sensation. The milk used for Toblerone is collected fresh from Swiss dairies, dried into powdered form through spray drying towers, and tested for purity, flavor, and fat content. Milk powder is a crucial element that lends Swiss chocolate its creamy, delicate profile. In addition to milk chocolate, Toblerone contains honey and almond nougat, which must also be manufactured with precision. The nougat is produced by mixing ground almonds, sugar, egg white, and honey, which are cooked to a stable yet chewy consistency. This nougat is then cooled, solidified, and broken down into small, crunchy pieces that can later be blended with chocolate. To achieve the consistent particle size required, nougat fragments are milled in special grinding machines and screened through sieves to ensure no overly large chunks remain. These pieces must be uniform so that every bite of a Toblerone bar has the same texture. Once all the raw materials are prepared, the actual chocolate making begins. In the mixing phase, cocoa liquor, cocoa butter, milk powder, sugar, and emulsifiers are blended in large stainless steel vats equipped with heavy-duty paddles. The proportions are carefully controlled by automated dosing systems linked to computerized recipes. At this stage, the nougat and honey are not yet introduced because the base chocolate must first go through refining and conching processes to achieve the correct texture. The mixed chocolate is passed through a series of 5-roll refiners, massive machines with rollers set at progressively tighter gaps. This action grinds the solid particles down to around 20 microns in size, small enough that the tongue cannot detect any graininess. After refining, the powdered chocolate mass is placed into conches, large trough-like machines fitted with rotating arms that knead, aerate, and heat the mixture. Conching can last from several hours to over a day, depending on the desired flavor development. During this time, volatile acids are driven off. The particles become evenly coated with fat, and the chocolate develops its characteristic smoothness and balanced flavor. Only after the conching process is complete are the honey and nougat pieces gently incorporated. This timing ensures that the delicate flavors of honey remain intact and that nougat pieces maintain their crunch without being broken down by extended mechanical agitation. Once the full mixture is ready, the chocolate must be tempered. Tempering is an essential process in chocolate manufacturing because cocoa butter can crystallize in several different forms, some of which produce dull, crumbly chocolate rather than glossy, snappy bars. In industrial tempering machines, the chocolate mass is cooled and reheated in a controlled sequence so that the stable form of cocoa butter crystals dominates. This process ensures that Toblerone has a shiny surface, a crisp snap, and does not melt prematurely during storage. With the chocolate tempered, the forming process begins. Unlike standard chocolate bars, Toblerone requires specialized molds shaped into its iconic triangular peaks. These molds are usually made from polycarbonate or food-grade stainless steel. Tempered chocolate with embedded nougat pieces is pumped into the molds using automated depositor heads that fill each cavity with the precise amount of chocolate. To ensure the chocolate fully fills the peaks and valleys, the molds are vibrated mechanically, which releases trapped air bubbles and distributes the mixture evenly. The filled molds then travel along a cooling tunnel, a long conveyor housed in a refrigerated chamber where controlled airflow brings the chocolate down to a stable temperature and solidifies it without causing surface defects. Once cooled and hardened, the bars are removed from the molds by automated demolding machines that gently flex or tap the molds to release the chocolate. These freshly formed Toblerone bars are now ready for packaging, but before that, they undergo stringent quality checks. Automated vision systems scan each bar for surface defects, broken peaks, or air holes, while weight sensors confirm that each bar meets precise specifications. Samples are also tested in quality control laboratories, where technicians measure fat content, melting behavior, and flavor consistency against reference standards. Packaging Toblerone presents another interesting challenge because of its shape. The triangular bar requires a distinctive triangular prism carton, which has become as iconic as the chocolate itself. In the factory, automated carton forming machines fold and glue flat cardboard blanks into their three-dimensional prism shapes. Meanwhile, chocolate bars are wrapped in foil or paper to preserve freshness and protect them from contamination. Robotic arms then insert the wrapped bars into the triangular cartons at high speed. High-resolution printers add branding, logos, nutritional information, and batch codes directly onto the cartons. Sealed cartons are checked once again by sensors to ensure proper closure before being loaded into larger shipping cases. The packaged Toblerone bars are stacked onto pallets using automated palletizing systems. From here, they are transferred into climate-controlled warehouses where temperature and humidity are carefully maintained to prevent bloom or texture loss. Distribution logistics then take over, with pallets loaded onto trucks, trains, or containers for shipment worldwide. Throughout transport, maintaining cool and dry conditions is essential since chocolate is sensitive to fluctuations that can cause whitening or melting. Retailers ultimately receive the bars, place them on shelves, and consumers across the globe recognize them instantly by their unique triangular boxes. Beyond the mechanics, the production of Toblerone highlights the integration of tradition and technology. The recipe remains faithful to its early 20th century origins, with Swiss milk chocolate, honey, and nougat at the core. Yet the scale, precision, and automation in today's factories allow millions of identical bars to be produced annually. Every piece of equipment, from conches to molding lines, is designed to ensure consistency and quality on a massive scale while still protecting the integrity of the original idea. The story of Ferrero Rocher begins in Italy, where the Ferrero company, already famous for products such as Nutella, Kinder chocolates, and Tic Tacs, sought to create a premium confection that combined texture, flavor, and an elegant presentation. Introduced in the 1980s, Ferrero Rocher quickly became a global success, celebrated both for its taste and for the distinctive gold-wrapped packaging that evoked luxury and indulgence. the brand capitalized on the image of a special occasion treat, often presented in clear plastic boxes as a gift rather than consumed casually, like standard candy bars. Behind this seemingly simple product lies a surprisingly complex and carefully engineered manufacturing process. The core of Ferrero Rocher is the hazelnut. Hazelnuts are grown primarily in Turkey, Italy, and other temperate regions, and Ferrero is one of the largest global purchasers of this nut. Quality control begins right at the source. Hazelnuts are harvested, sorted, and dried, then shipped to processing facilities where they are tested for size, flavor, and absence of defects. At the factory, the nuts are roasted in large drum or fluidized bed roasters, a step that enhances their flavor by developing nutty, caramelized notes while also reducing moisture content. Automated systems monitor roasting temperature and time to ensure uniform results, since even slight variations can affect flavor consistency. Once roasted, the hazelnuts are cooled, stored under controlled humidity, and eventually fed into the production lines. Each Ferrero Rocher chocolate begins with a single whole hazelnut, which forms the central core of the confection. Hazelnuts destined for the center are inspected once more to ensure they are intact and properly sized. These nuts are then aligned and portioned using vibratory feeders and precision dispensers so that each chocolate receives one whole hazelnut without exception. Surrounding the hazelnut core is a thin, delicate layer of chocolate cream. This filling is essentially a version of hazelnut praline, a paste made by grinding roasted hazelnuts with sugar and blending it with cocoa powder and vegetable fats to achieve a smooth, creamy texture. The cream is manufactured in large mixing tanks fitted with high shear blades to homogenize the mixture. Precise dosing pumps then deliver just the right amount of this cream around each hazelnut, creating the first layer of indulgence. Automated forming systems encase the nut with cream by depositing the filling into hemispherical molds, placing a nut inside and capping it with more cream, producing a complete sphere with the nut suspended at its center. Once this creamy core has been formed, it is encased within a thin, crisp wafer shell. This is one of the most technically intriguing steps of Ferrero Rocher production. Wafer batter, made from wheat flour, water, and small amounts of oil or sugar, is prepared in large mixing vats, then deposited into heated wafer presses. These presses work much like industrial waffle irons, forming thin sheets of crispy wafer by baking at high temperatures until golden and brittle. The baked sheets are then trimmed and conveyed to shaping stations, where specialized machines stamp out hemispherical wafer cups. Each cream-filled hazelnut core is placed into one of these wafer cups, and a second wafer half is pressed onto the top, sealing the sphere. The result is a delicate, hollow wafer shell encapsulating the nut and cream filling. Excess wafer edges are carefully trimmed away by automated cutters to create a smooth, uniform sphere. At this point, the confection still lacks its outer chocolate and hazelnut coating. To prepare for this stage, the wafer balls are conveyed through enrobing lines. The first step involves a curtain of liquid milk chocolate through which the spheres pass, ensuring complete coverage. This coating acts both as a sealant to protect the wafer from moisture and as the base layer for the final crunchy coating. The chocolate used here is formulated specifically to achieve the right viscosity for enrobing. Too thin, and it would not provide adequate coverage. Too thick, and it would result in an uneven or clumpy surface. Immediately after being enrobed, the wet chocolate surface of the spheres is showered with finely chopped, roasted hazelnut pieces. These pieces are produced in the same factory by grinding roasted hazelnuts into small fragments using hammer mills and screening them to the desired particle size. Precision vibratory feeders sprinkle these fragments onto the freshly coated spheres, where they stick to the chocolate layer. The timing is critical. The nuts must adhere firmly before the chocolate begins to set. Once fully coated, the spheres pass through a second chocolate enrobing stage that seals the nut pieces into place, creating the distinctive rough, textured surface of Ferrero Rocher. The enrobed chocolates then enter a cooling tunnel, a long, refrigerated conveyor that gradually reduces the temperature of the product in controlled stages. Rapid cooling can cause cracks or fat bloom, so the temperature and airflow are carefully regulated to solidify the chocolate smoothly. By the time the spheres emerge from the tunnel, they are fully set and ready for packaging. Packaging is a vital part of Ferrero Rocher's appeal. The chocolates are wrapped individually in thin gold foil, which not only provides protection but also conveys a sense of elegance and exclusivity. Automated wrapping machines handle this delicate process. Each chocolate is positioned precisely on a sheet of foil, after which mechanical fingers fold and twist the foil snugly around the sphere. The top of the chocolate is decorated with a small circular label bearing the Ferrero Rocher logo. The wrapped chocolates are then placed into pleated brown paper cups that provide structural support and enhance the presentation. Once wrapped and cupped, the chocolates are arranged in their signature clear plastic boxes, often in patterns that maximize both aesthetics and space efficiency. Robotic arms or high-speed pick-and-place machines handle this task with great precision, ensuring that the chocolates are not damaged during packing. Lids are sealed onto the boxes, and decorative labels and logos are applied. These boxes are then grouped into larger cartons for transport and distribution. Throughout the entire process, stringent quality control measures are in place. Samples are taken at every stage to check for weight, size, flavor, and texture. Advanced vision inspection systems ensure that no product leaves the line with missing coatings, broken shells, or defective wrapping. Hazard control protocols are enforced under HACCP guidelines, with metal detectors and X-ray scanners checking for contaminants. Since hazelnuts are allergenic, factories maintain strict segregation and cleaning practices to avoid cross-contamination with other product lines. Storage and distribution of Ferrero Rocher also require careful attention. Chocolate products are sensitive to heat and humidity, which can cause melting, sugar bloom, or fat bloom. Factories and warehouses maintain controlled conditions of around 18 to 20 degrees Celsius with low humidity. From the warehouse, products are shipped worldwide by truck, container, or air freight, depending on demand and destination. Cold chain logistics ensure that chocolates arrive at retailers in pristine condition. What makes Ferrero Rocher remarkable is how its production combines advanced industrial automation with the appearance of artisanal craftsmanship. Each piece feels handmade because of its individual wrapping and layered textures, yet in reality, every step is driven by highly specialized machinery capable of producing thousands of chocolates per hour. The golden foil, the delicate paper cup, the precision placement in plastic boxes, all of these details contribute to the perception of luxury, but they are achieved through meticulously engineered automation. The success of Ferrero Rocher also lies in the balance of textures created by the layered construction. The crunch of the outer hazelnut-coated chocolate shell gives way to the light crispness of the wafer, followed by the smooth, creamy praline, and finally, the whole roasted hazelnut at the center. Each of these elements requires different processing conditions, yet they must come together in perfect harmony in every piece. Achieving this consistently across millions of units each day is a testament to the sophistication of modern confectionery engineering. The story begins with sourcing the most important ingredient of all, the cocoa bean. Lindt maintains strict control over the origins of its cocoa supply, working directly with farming communities in West Africa, Central and South America, and other equatorial regions. Cocoa trees bear pods that are harvested, split open, and filled with cocoa beans surrounded by pulp. These beans are fermented in large piles or boxes covered with banana leaves to trap heat, where natural yeasts and bacteria convert sugars into acids that develop the characteristic chocolate flavor precursors. After several days of fermentation, the beans are dried in the sun to reduce their moisture content before being bagged and shipped overseas to Europe. Once the cocoa beans arrive at Lindt's factories, quality control is paramount. Samples are taken from each batch and roasted in laboratory test roasters to evaluate flavor potential. Beans are graded for size, moisture, aroma, and absence of defects. Only the best lots are accepted into production. The accepted beans are then cleaned to remove debris such as dust, stones, or fibers before entering the roasting stage. In industrial-scale drum roasters, the beans are heated at carefully controlled temperatures that coax out the complex flavors. Roasting is one of the most critical steps as it defines the final taste profile. Too light, and the chocolate will be weak and acidic. Too dark, and it may become bitter or burnt. After roasting, the beans are cracked open in specialized breaking machines. These machines use a combination of rollers and air separation to break the beans into nibs while blowing away the lighter husks. The nibs are the true treasure, composed of cocoa solids and cocoa butter. They are then ground in massive stone or steel mills until they release their fat and form a thick, dark liquid known as cocoa liquor. This liquor can either be used directly in chocolate or pressed hydraulically to separate it into cocoa butter, the fat component, and cocoa solids, which are later milled into cocoa powder. Milk and sugar are the next essential components of Lindt's milk chocolate products. Fresh milk from Swiss dairies is delivered and processed into milk powder using spray drying technology. Sugar, usually sourced from European sugar beets or imported cane sugar, is refined to an extremely fine crystal size. The cocoa liquor, cocoa butter, milk powder, and sugar are combined in large stainless steel mixers. At this stage, the mixture is still coarse and granular. To create the silky smoothness for which Lindt is renowned, it must undergo refining. Refining occurs in 5-roll mills, towering machines equipped with rollers that are set progressively closer together. The chocolate mass passes through each roller gap, which crushes the sugar and cocoa particles smaller and smaller until they reach a size of about 20 microns. This is smaller than the sensitivity of the tongue, so the final chocolate feels smooth and creamy instead of gritty. The finely ground mass is then ready for the process that made Lindt famous, conching. Conching is the heart of Lindt chocolate production. Originally, Rodolphe Lindt developed the technique by accident, leaving his mixer running over the weekend. The result was a chocolate with unprecedented smoothness and richness. In modern factories, conching is carried out in massive steel troughs with rotating arms that knead, agitate, and aerate the chocolate mass for hours or even days. During this time, volatile acids are evaporated, particles are coated with cocoa butter, and the mass becomes fluid and homogeneous. The friction of the conching arms generates heat, which helps drive off unwanted flavors and develops a balanced, mellow profile. Different Lindt products undergo different durations of conching, giving rise to the nuanced flavor differences across their range. Once the chocolate has been conched to perfection, it must be tempered. Cocoa butter is a polymorphic fat, meaning it can crystallize in several different forms. Only one of these forms, known as the stable beta crystal, gives chocolate its glossy sheen, sharp snap, and resistance to bloom. Industrial tempering machines cool and reheat the chocolate in carefully controlled steps, encouraging only the stable crystal form to develop. This process requires absolute precision, as improper tempering can ruin the texture and appearance of the final chocolate. After tempering, the chocolate is ready to be formed into products. For standard chocolate bars, the tempered chocolate is pumped into polycarbonate molds, shaped according to Lindt's signature designs. The molds pass through vibrating stations that remove air bubbles and ensure an even fill. They then travel along cooling tunnels where controlled airflow and refrigeration gradually solidify the chocolate. Once hardened, the bars are ejected from the molds by mechanical tapping or flexing, inspected for defects, and transferred to packaging lines. For Lindt's famous Lindor truffles, the process is more intricate. These confections feature a delicate chocolate shell that encloses a smooth, flowing filling. The shell is created by spinning tempered chocolate inside spherical molds, forming a thin but strong layer. Once the shells are hardened, a liquid filling made of chocolate blended with additional cocoa butter and sometimes cream is injected into the center. The spheres are sealed with more chocolate and cooled again to set. When consumers bite into a Lindor truffle, the outer shell gives way to the luxuriously melting filling, a sensation created through meticulous engineering. After molding, forming, or enrobing, packaging becomes the next crucial stage. Lindt bars are wrapped in foil and paper sleeves that maintain freshness while presenting a premium look. Lindor truffles are individually wrapped in colored foils, twisted at the ends to create an elegant presentation. Automated wrapping machines perform this at high speed while ensuring consistency. The wrapped chocolates are then boxed, labeled, and grouped into cartons for shipping. Each package bears batch codes for traceability, and automated vision systems check alignment and sealing before boxes leave the factory. Throughout the entire process, quality control is relentless. Every batch of cocoa liquor is tasted and analyzed for flavor balance. Samples of conched chocolate are tested for viscosity, fat content, and particle size. Finished products are checked for gloss, snap, and uniformity. Food safety is upheld through rigorous hygiene protocols, allergen control, and HACCP systems. Metal detectors and X-ray scanners ensure that no foreign objects contaminate the products. Distribution is the final step in Lindt Chocolate's journey. Products are stored in climate-controlled warehouses where temperature and humidity are carefully monitored to prevent bloom or melting. From there, chocolates are shipped worldwide in refrigerated containers or trucks. Retailers receive them in pristine condition, and consumers encounter them either in Lindt boutiques, luxury stores, supermarkets, or duty-free shops across the globe. What sets Lindt apart from many other chocolate manufacturers is its combination of historical craftsmanship and cutting-edge automation. The conching process, pioneered by Rodolphe Lindt, remains central, yet the scale has grown to thousands of tons per year. Sophisticated dosing systems, computer-controlled tempering units, and robotic packaging lines ensure absolute consistency, while the company's commitment to quality and sourcing upholds its reputation. The result is chocolate that tastes handmade, yet is produced in enormous quantities. Nutella's key ingredients are hazelnuts, sugar, palm oil, cocoa solids, skimmed milk powder, whey powder, lecithin as an emulsifier, and vanillin as a flavoring agent. Each of these ingredients is sourced globally, selected for consistency, taste, and availability. Hazelnuts, the signature ingredient, are predominantly sourced from Turkey, which produces more than 2/3 of the world's supply. However, Italy, Chile, and the United States also contribute to the global hazelnut harvest. Ferrero, the company behind Nutella, maintains long-term relationships with growers and has implemented traceability programs to ensure that hazelnuts meet quality standards for moisture content, size, and taste. Upon arrival at the processing facility, hazelnuts go through rigorous inspection and sorting procedures. This is a critical control point because the quality of the nut directly affects the flavor and texture of the final product. Optical sorters and vibrating sieves are used to remove debris, stones, and underdeveloped nuts. The selected hazelnuts are then subjected to a deshelling operation using mechanical crushers that crack the shells without damaging the kernels. These kernels are further inspected and cleaned before being sent to large-scale roasting units. Roasting is one of the most important flavor development stages in Nutella production. In industrial operations, continuous roasting ovens are used. where hazelnuts travel through a rotating drum or along a conveyor belt under a flow of hot air, typically between 140 to 160 degrees Celsius. Roasting duration and temperature are carefully controlled to bring out the nutty aroma and to reduce moisture to below 5%. After roasting, the nuts are cooled quickly to preserve their volatile aromatic compounds and prevent overcooking. The cooled hazelnuts are then transferred to grinding machines, where they are ground into a paste using roller mills and high-speed grinders. The result is a fine hazelnut paste with a smooth texture ready to be incorporated into the final mix. Meanwhile, other key ingredients are prepared in parallel. Sugar, which makes up a significant portion of the spread, is delivered in bulk as granulated white sugar. Before use, the sugar is pulverized in industrial fine grinders or pin mills until it becomes a powdered form with consistent particle size, often below 30 microns, to avoid any grittiness in the final texture. This powdered sugar is stored in silos and fed into the mixing tanks using pneumatic conveying systems. Cocoa solids, another essential ingredient, are typically received as cocoa powder. This powder undergoes sifting and magnetic separation to remove any foreign particles or metallic fragments. Skimmed milk powder and whey powder, both derived from dairy processing, are reconstituted into a slurry with water or added in dry form depending on the plant design. These milk-based ingredients contribute not only to flavor, but also to the creamy mouthfeel and protein content of the spread. Palm oil is selected for its semi-solid consistency at room temperature, which is ideal for producing a spreadable product that does not require refrigeration. Before blending, palm oil is filtered and heated to a controlled temperature to ensure uniform mixing. It is pumped into heated storage tanks, where it is kept in liquid form and circulated to prevent crystallization. Once all base ingredients are prepared, the process of mixing begins in large-scale stainless steel mixing tanks. These tanks are fitted with high-torque agitators and precision load cells that measure the exact quantity of each ingredient added. The powdered sugar, hazelnut paste, cocoa powder, milk powder, and palm oil are introduced sequentially, followed by small quantities of lecithin and vanillin. Lecithin acts as an emulsifier, allowing the fat-based palm oil to bind with the water-based milk components, ensuring the product remains stable and homogeneous. Vanillin, a synthetic or natural flavoring, gives Nutella its distinct sweet aroma. The mixture is subjected to a refining process to achieve the desired texture and particle size. This is often accomplished using 5-roll refiners or conching machines. The 5-roll refiner uses a series of precision-engineered steel rollers that progressively grind the mixture to a fine, uniform consistency, typically achieving particle sizes of around 20 microns. This stage is crucial for eliminating any detectable graininess, resulting in the smooth, velvety texture Nutella is known for. In some facilities, a conching step follows refining. In conching, the mixture is kneaded and aerated for several hours in large heated vessels. The process further develops flavor, reduces acidity, and allows volatile off flavors to evaporate. Temperature, shear force, and mixing speed are all tightly controlled to maintain product consistency. After conching, the mixture is cooled slowly to prevent separation and to stabilize the emulsion. Once the spread reaches the correct viscosity and temperature, it is pumped through sanitary pipelines to the filling stations. Filling lines are fully automated and consist of synchronized conveyor systems, rotary fillers, and capping machines. The jars, made from glass or plastic, are cleaned with compressed air or ionized air blowers before being filled. Filling heads dispense the exact amount of Nutella into each jar with remarkable precision, ensuring minimal variation between units. Immediately after filling, jars pass through a sealing station, where a foil membrane is applied to the mouth of the jar. This step is critical for maintaining freshness and preventing microbial contamination. The foil seal is typically induction sealed using a non-contact electromagnetic process that heats the foil and causes it to bond to the jar rim. Once sealed, the jars are capped with tamper-evident lids and conveyed to labeling machines. High-speed labelers apply brand-specific labels with information such as batch number, expiration date, and ingredients. Each jar then proceeds through a series of quality control checkpoints. These include weight checks, vision systems to verify correct sealing and labeling, and metal detection to ensure product safety. Defective units are automatically rejected and diverted for reprocessing or disposal. The entire packaging area is designed with hygiene in mind, using positive air pressure zones, clean-in-place systems, and stainless steel surfaces to reduce contamination risk. After packaging, Nutella jars are grouped into cartons or shrink-wrapped multi-packs, then stacked on pallets using robotic arms. Pallets are stretch-wrapped and labeled with barcodes for inventory tracking. From here, the product enters the distribution phase. Nutella's distribution logistics are a finely tuned operation. Pallets are stored temporarily in climate-controlled warehouses where temperature and humidity are maintained to prevent oil separation or spoilage. Inventory management systems track product movement using real-time data. Distribution centers coordinate with retailers, wholesalers, and export logistics to move products efficiently. Nutella is shipped in refrigerated or insulated containers only when necessary, though its high fat, low moisture content gives it considerable shelf stability. Throughout its supply chain, Nutella maintains compliance with international food safety standards such as ISO 22000, BRC, and HACCP protocols. Auditors regularly inspect facilities for compliance, and the entire process from hazelnut sourcing to jar sealing is documented for traceability and recall readiness. Automation, data collection, and machine learning are increasingly used to optimize processes, predict maintenance needs, and reduce waste. What makes Nutella's production so compelling is the precise synchronization of global sourcing, advanced food engineering, and automation technologies that allow for the consistent output of millions of jars per day. Every batch is a result of not just culinary science, but also the collaboration of agronomists, engineers, food technologists, and supply chain experts. Beyond the factory floor, Nutella's evolution continues with reformulations aimed at reducing sugar or incorporating more sustainable palm oil. Efforts to use recyclable packaging and implement blockchain for ingredient tracking reflect broader industry trends towards transparency and environmental responsibility. The foundation of Jif begins with its primary ingredient, peanuts. Specifically, the variety used in commercial peanut butter production is often the runner peanut, prized for its uniform kernel size, mild flavor, and high oil content. These peanuts are primarily grown in the southeastern United States, including states like Georgia, Alabama, and Florida, where sandy soils and warm climates create optimal growing conditions. Jif, owned by the J.M. Smucker Company, works closely with peanut growers through long-standing contracts to ensure consistent quality and supply. Before the peanuts even reach the factory, they're subjected to extensive grading systems operated by the USDA, evaluating factors like kernel size, moisture content, and damage from mold or pests. Once harvested, the raw peanuts are cured by drying them to a safe moisture level, usually around 10%. This drying stage is essential to prevent mold growth during transport. The peanuts are then shelled using mechanical shellers that crack the outer holes while leaving the kernels intact. After shelling, the peanuts are cleaned using air classifiers and vibrating screens to remove debris, dirt, and remaining shell fragments. These cleaned kernels are then transported in bulk to Jif's dedicated peanut butter production facilities, where their transformation truly begins. Upon arrival at the factory, peanuts undergo a second round of cleaning and quality control. Optical sorters equipped with high-speed cameras and sensors scan each peanut at astonishing rates, removing any discolored, damaged, or foreign material contaminated nuts. Metal detectors are also employed at this stage to ensure there are no traces of metal debris from harvesting equipment. These steps are critical not only for food safety, but also for maintaining Jif's smooth and consistent flavor. The next stage is roasting, arguably the most important phase for flavor development. Industrial peanut roasters are highly sophisticated machines capable of handling thousands of pounds of peanuts per hour. Jif uses a continuous dry roasting process where peanuts are evenly fed onto a perforated conveyor belt that moves through a tunnel of hot, forced air. Temperatures during roasting typically range between 160 and 180 degrees Celsius, with exact values finely tuned based on peanut size, oil content, and desired flavor profile. This process typically takes 15 to 30 minutes and is closely monitored using infrared sensors and real-time moisture analyzers. As peanuts roast, their proteins and sugars undergo Maillard browning, creating hundreds of volatile aroma compounds that contribute to peanut butter's distinctive roasted flavor. Immediately after roasting, the peanuts are rapidly cooled using chilled air blowers to stop the cooking process and lock in the developed flavors. This cooling also prevents oil separation and oxidation, both of which can negatively impact product shelf life. At this point, the roasted peanuts are ready to be ground, but first they must be blanched. Blanching in peanut butter production refers not to cooking in water, but to the mechanical removal of the thin, papery red skins that surround the kernels. In Jif's facilities, peanuts are sent through dry blanchers, machines that tumble the nuts at high speeds while heated air loosens the skins. Rotating brushes then remove the skins entirely, and high-capacity vacuum systems suck away the debris. The blanched peanuts are now a light golden color and are inspected one final time before grinding. The grinding stage is where peanuts are turned into a thick, luscious paste. Jif's production lines use a two-stage grinding process to achieve the brand's famously smooth consistency. First, peanuts are coarse ground using heavy-duty industrial grinders. These machines use stainless steel burrs or hammer mills to crush the nuts into a semi-solid mass known as peanut paste. This paste still contains some coarse particles and has not yet achieved its final texture. Next, the coarse paste is fed into ultra-high-speed fine grinders, often colloid mills, which apply extreme shear forces to reduce particle size down to 10 to 15 microns. This is a crucial target, as particle size below 20 microns ensures a mouthfeel that is perceived as completely smooth by consumers. During this stage, other ingredients are also introduced into the mixture. These include sugar, fully hydrogenated vegetable oils, salt, and sometimes molasses, or mono and diglycerides. The oils, often made from rapeseed, cottonseed, or soybean, are used to stabilize the peanut butter and prevent oil separation on the shelf. Unlike palm oil or liquid vegetable oil, fully hydrogenated oils remain solid at room temperature and help give Jif its stable texture without requiring stirring. These additional ingredients are metered in with extraordinary precision using automated dosing systems connected to load cells and flow meters. Inline mixers ensure that each component is fully dispersed throughout the peanut paste. The temperature during grinding is carefully controlled, typically held between 60 and 75 degrees Celsius, to keep the product fluid without degrading flavor compounds. Once the peanut butter has been ground to the desired texture and all ingredients are thoroughly incorporated, it enters a holding tank under nitrogen blanketing. This protective gas layer prevents oxidation and helps preserve freshness during the short holding period before packaging. The product is then pumped to the filling lines through a network of heated sanitary stainless steel piping. Jif's packaging lines are models of efficiency and automation. Plastic jars, blow molded from PET or HDPE, are automatically unscrambled and conveyed into position. Before filling, jars pass through an air rinse station that uses ionized air to remove dust or plastic fragments. High-speed rotary piston fillers dispense precise volumes of peanut butter into each jar, minimizing air entrapment to avoid spoilage and maintain shelf life. Filled jars are then capped immediately using torque-controlled capping heads that screw on tamper-evident lids. After capping, jars pass through induction sealers where a foil membrane is bonded to the jar rim. This step uses electromagnetic energy to heat and seal the foil in milliseconds, creating a hermetic barrier that locks in flavor and protects against microbial contamination. The sealed jars move to labeling machines, where front and back labels are applied, followed by laser or inkjet printers that mark each jar with batch codes, production dates, and plant IDs. Throughout this packaging process, quality control is constant and rigorous. Automated vision systems inspect each jar for correct fill height, proper labeling, and cap placement. Metal detectors and X-ray scanners identify any contamination before product leaves the factory. Random samples are also pulled for texture analysis, oil separation testing, sensory panels, and microbiological screening. Any deviation from specifications leads to immediate corrective actions, and defective jars are removed from the line. Packaged jars are grouped into corrugated cardboard cases using robotic case packers. These cases are palletized by programmable robotic arms and stretch wrapped to ensure stability during transport. Each pallet receives a barcode label integrated into Jif's warehouse management system, allowing for real-time traceability from production to point of sale. Once palletized, the finished peanut butter is moved to distribution centers equipped with temperature and humidity control. Although Jif peanut butter is shelf-stable and does not require refrigeration, maintaining moderate temperatures during warehousing and shipping helps preserve flavor and prevent oil migration or texture degradation. From these central hubs, Jif is shipped to retailers, wholesalers, and export customers across the country and around the globe. The journey from raw peanut to finished jar is guided not only by mechanical precision, but also by a deep understanding of food chemistry, microbiology, logistics, and consumer expectations. Behind the familiar red-lidded jar is a network of engineers, food scientists, supply chain analysts, and production operators, all working in synchrony to ensure that every spoonful of Jif meets exacting standards. Advancements in automation and data analytics continue to refine the process. Modern Jif facilities are equipped with real-time monitoring systems, predictive maintenance software, and even machine learning algorithms that optimize roasting profiles based on moisture content and kernel density. Environmental controls ensure energy efficiency and waste reduction, and partnerships with peanut growers include sustainability initiatives aimed at soil conservation and water use reduction. The story of Hershey's syrup begins with its core ingredients: cocoa, sugar, water, corn syrup, salt, preservatives, and a few functional additives like potassium sorbate and xanthan gum. Each of these components is sourced with meticulous care to ensure consistency and food safety. Cocoa powder, the primary flavoring agent, is typically sourced from West Africa, where the Hershey Company partners with certified cooperatives to encourage sustainable farming practices. The cocoa beans are fermented, dried, and shipped to the US, where they are roasted, ground, and pressed into cocoa cake. This cake is then pulverized into a fine cocoa powder, standardized for fat content, flavor profile, and color intensity. Upon arrival at Hershey's syrup production facilities, all ingredients undergo rigorous testing. The cocoa powder is checked for microbiological safety, color consistency, particle size, and moisture levels. Sugar, often in granulated form, is tested for crystal uniformity, purity, and absence of foreign materials. Corn syrup, used as both a sweetener and thickener, is delivered in tanker trucks and stored in heated silos. It is continuously circulated to prevent crystallization or microbial growth. Water used in the process is treated on-site, filtered, softened, and sanitized using UV light or reverse osmosis to ensure purity and microbial control. The first major production stage is blending the dry and liquid ingredients. The process typically starts with the creation of a sugar corn syrup slurry. In large stainless steel jacketed mixing tanks, granulated sugar is combined with warm water and corn syrup under controlled agitation. These tanks are equipped with variable speed mixers and internal temperature sensors to maintain optimal dissolution rates. The heating jackets help bring the mixture to a consistent temperature, usually between 55 and 70 degrees Celsius, to accelerate solubility while avoiding caramelization. Once a uniform syrup base is achieved, cocoa powder is added. However, dry cocoa is notoriously difficult to hydrate due to its high fat content and fine particle size, which cause it to float and form lumps when introduced to liquid. To overcome this, Hershey's production lines utilize high shear mixers and vacuum-powered powder feeders. The vacuum system pulls cocoa powder directly into the liquid stream, minimizing clumping and ensuring uniform dispersion. Simultaneously, high-speed rotor-stator mixers or inline homogenizers shear the mixture at thousands of RPMs, breaking down any agglomerates and producing a velvety, uniform chocolate syrup base. At this stage, salt and preservatives such as potassium sorbate are also introduced. These additions are precisely dosed using automated ingredient hoppers that weigh each component before releasing it into the blanders. Potassium sorbate acts as a mold and yeast inhibitor, extending the product's shelf life. Some formulations may also include citric acid or sodium citrate to adjust pH, which affects both microbial stability and flavor brightness. The syrup then enters the cooking phase. Unlike batch cooking in traditional kitchens, industrial syrup production uses continuous flow heating systems. The chocolate slurry is pumped through tubular or plate heat exchangers, where it is heated rapidly to pasteurization temperatures, typically between 85 and 95 degrees Celsius. This thermal treatment destroys any remaining microbial contaminants and activates the emulsifiers and stabilizers added in earlier steps. The product is held at this temperature for a specific dwell time as it flows through holding tubes, ensuring regulatory compliance with pasteurization standards. After cooking, the syrup must be cooled quickly to prevent overcooking and maintain the desired viscosity and flavor. This is achieved using chilled water heat exchangers, which rapidly bring the syrup down to below 30 degrees Celsius. Rapid cooling also helps stabilize the emulsion, locking in the texture and preventing ingredient separation. The cooled syrup is then transferred to intermediate holding tanks, where it is gently agitated and blanketed with nitrogen gas to minimize oxidation. At this point, the syrup undergoes several quality control checks. Samples are pulled and tested for viscosity using rotational viscometers, ensuring that the pourability matches the brand's standard profile. Colorimeters assess chocolate intensity and hue, while refractometers measure sugar concentration. In parallel, sensory panels may be employed to evaluate flavor, mouthfeel, and aroma. Microbial testing is conducted on every batch to confirm that pasteurization was effective and that no contamination has occurred. Once the product passes quality control, it is sent through final filtration before packaging. Fine mesh inline filters remove any particulate matter that may have formed during cooking or cooling. This ensures a perfectly smooth syrup with no grit or undissolved solids. Packaging Hershey's syrup involves a highly synchronized series of steps designed for both hygiene and speed. The most common containers are squeezable plastic bottles, which are blow molded from PET or HDPE on site or delivered pre-formed. These bottles are first conveyed through an air rinse system that blasts ionized air to remove dust or debris. They are then indexed into position beneath the filling nozzles. Filling is performed using servo-controlled, volumetric, or piston fillers. These machines are calibrated to deliver exact quantities of syrup, typically in the range of 650 to 800 grams per bottle, depending on size. The syrup is dispensed at controlled speeds to prevent splashing or air entrapment. No-drip filling heads are often used to maintain clean bottle exteriors and reduce product waste. After filling, the bottles move to the capping station. Caps are sorted using centrifugal feeders and applied using torque-monitored capping heads, which ensure a tight seal without over-tightening. Each bottle is then passed under an induction sealer, where an aluminum foil seal is bonded to the bottle mouth using electromagnetic heating. This tamper-evident seal not only enhances shelf life, but also guarantees product integrity. Next, the bottles pass through a labeling machine where pressure-sensitive labels are applied with exacting precision. Labels include not just branding and nutrition information, but also critical traceability codes, including batch numbers, timestamps, and plant identifiers. These details are laser-etched or printed using inkjet coders. Before leaving the line, every bottle passes a series of automated inspection stations. Vision systems equipped with high-speed cameras check for correct fill levels, cap placement, seal integrity, and label alignment. Any non-conforming product is rejected and diverted to a separate inspection area for manual review. Approved bottles are grouped into cartons or shrink-wrapped multi-packs. Robotic case packers load the bottles into boxes, which are then sealed, labeled, and palletized. These pallets are stretch-wrapped and tagged with scannable barcodes for warehouse tracking. The entire process from filling to palletization is fully integrated into Hershey's manufacturing execution system, allowing for real-time monitoring and inventory control. Palletized syrup is transported to climate-controlled distribution centers. While Hershey's syrup is shelf-stable, temperature extremes can still impact viscosity and appearance. Warehouses maintain stable conditions to prevent thickening in cold weather or oil separation in high heat. From there, the product is dispatched to retail partners, online fulfillment centers, and export destinations. Throughout the supply chain, Hershey's implements strict food safety protocols, including compliance with the Global Food Safety Initiative, hazard analysis and critical control points, and FDA regulations. Traceability is maintained from raw cocoa bean to finished bottle, ensuring any issue can be traced and contained within hours. What makes Hershey's syrup so enduring in the marketplace isn't just its flavor, it's the precision and consistency made possible through modern food engineering. Every step of the process, from the aggressive mixing of cocoa powder to the final induction seal, is executed with scientific rigor. Equipment calibration, ingredient testing, and continuous improvement protocols ensure that each bottle tastes the same, pours the same, and satisfies the same cravings generation after generation. As the brand moves forward, sustainability is becoming an even greater focus. Efforts to reduce plastic use in packaging, improve energy efficiency in heating and cooling systems, and source more ethical cocoa are all part of Hershey's long-term production goals. Some lines are exploring bio-based PET alternatives for bottles and increasing recycling within plant operations. Continuous feedback from quality assurance teams and customer satisfaction metrics are used to refine processing parameters and optimize flavor retention across product shelf life. The history of Nerds stretches back to the early 1980s, when they were first introduced to the market as a playful, intensely flavored treat unlike anything else in the candy aisle. The appeal lay in their irregular shapes, their bright colors, and their signature combination of sweet and sour notes. Behind the scenes, however, the magic is created not by whimsy, but by a carefully controlled industrial process. It all begins with the sourcing of raw ingredients. The foundation of Nerds is refined cane or beet sugar, which arrives at the factory in bulk deliveries, often in multi-ton silos or in large paper sacks that are emptied into storage hoppers. This sugar is highly refined to ensure purity, with a moisture content so low that it will not clump during storage or handling. Alongside the sugar come shipments of corn syrup, which acts as a binding and texturing agent, as well as citric acid and malic acid to provide the tartness that defines Nerds' flavor profile. The plant also receives concentrated flavor oils and powdered colors approved for food use. Each batch of these ingredients is tested in a quality control laboratory before it enters the production stream, ensuring compliance with both flavor and safety standards. The production of Nerds begins with a core, which is essentially a tiny granule of sugar that serves as the seed for the candy's build-up process. These seed crystals are often derived from slightly coarser sugar grains that have been screened to a uniform size. The real artistry begins in the heart of the coating pans, large rotating drums that are the beating heart of sugar candy manufacturing. Inside these stainless steel pans, the sugar seed crystals are gently tumbled as a fine mist of sugar syrup is sprayed over them. This syrup is prepared in a heated mixing tank, where granulated sugar is dissolved into water under controlled temperature, often in the range of 110 to 130 degrees Celsius, and then blended with a precise amount of corn syrup to control crystallization. The hot syrup flows through jacketed piping to prevent premature cooling before being atomized into a fine spray within the coating pan. As the syrup coats the tumbling seed crystals, it begins to harden upon contact with the cooler air inside the pan, forming a thin outer layer. Then, a light dusting of dry sugar is sometimes added to further build the surface and maintain separation between individual granules. This cycle repeats dozens or even hundreds of times, each layer adding microns of thickness to the growing candy piece. Operators closely monitor airflow, humidity, and drum rotation speed to ensure that the candies do not stick together or form unwanted lumps. During this stage, the irregular shapes that make Nerds so distinctive begin to emerge. Unlike machine-molded candies that have identical geometry, these sugar-coating pans produce slight variations in size and contour, which means every Nerd has its own unique outline. The gradual layering process continues until the candy reaches the target size, which is typically just a few millimeters in diameter. Once the base size is achieved, flavoring and coloring are introduced. This is a delicate operation, as liquid flavors and colorants must be distributed evenly without dissolving the sugar surface. The pan operator reduces airflow slightly and sprays a concentrated solution of flavor oils, acids, and color onto the candy bed. In many cases, flavors are applied in small incremental sprays with pauses for tumbling in between, allowing the surface to dry and preventing color streaking. The flavors are carefully balanced so that the acids provide tang without overwhelming the sweetness, creating the signature taste that fans recognize instantly. After flavoring and coloring, the candies undergo a polishing step. This involves applying a thin layer of glazing agent, such as carnauba wax, which gives the Nerds their characteristic sheen and helps protect them from moisture pickup during storage. The glaze is applied in a separate polishing pan, where candies are tumbled with a small amount of the molten wax until every piece has a uniform shine. At this point, the candies are allowed to cool and set fully, ensuring that their coatings have hardened completely. Cooling may occur in ambient air or in a temperature-controlled chamber that maintains low humidity to prevent stickiness. The fully cooled candies are then transferred via gentle vibratory conveyors to the packaging area. The packaging operation for Nerds is an impressive example of precision weighing and high-speed filling. Because the candy pieces are so small and irregular, multi-head weighers are commonly used to ensure accurate portioning. These machines use multiple load cells arranged in a circular pattern, dropping small amounts of candy from each channel until the combined total matches the target weight. This system minimizes giveaway and ensures that each box contains exactly the promised amount. The iconic Nerds boxes are constructed from food-grade cardboard with an inner lining that protects against moisture. The packaging line begins by folding and gluing the flat printed cartons into their box shape, often with automated carton erectors that can handle hundreds of units per minute. The weighers then deposit the precise quantity of candy into each box through stainless steel chutes. For dual flavor boxes, a partition is inserted inside the carton and two separate weighing heads feed different candies into each side simultaneously. Once filled, the boxes pass through a closing station where flaps are folded and glued shut, followed by a coding station that prints lot numbers and best before dates for traceability. The sealed boxes are then collated into larger trays or shrink-wrapped bundles for ease of handling in distribution. Quality control continues all the way through the process. In addition to the raw ingredient checks at the start, samples of candy are pulled from the line at regular intervals to assess flavor consistency, color uniformity, and physical integrity. The hardness of the coating is measured with specialized instruments, and the acidity levels are checked to ensure the sourness remains within the brand's signature profile. Metal detectors are integrated into the conveyor system to ensure no foreign materials make their way into the final product. From the packaging area, the candies move to the warehouse for distribution. Since Nerds are low in moisture and have a hard sugar shell, they are relatively stable during storage. However, they are kept in a cool, dry environment to maintain their texture and prevent color fading. Pallets of finished product are wrapped and staged for shipment to wholesalers, retailers, and export markets around the world. The journey from sugar seed to the vibrant, tangy pellets in your hand is a testament to how much engineering is hidden inside even the simplest candies. Each step, from syrup spraying in massive tumbling pans to the delicate flavor infusion and high-speed filling lines, is executed with precision to deliver the playful, crunchy experience that has kept Nerds popular for decades. Over time, manufacturing technology for Nerds has evolved to improve efficiency and consistency. Early production relied heavily on skilled operators adjusting pans by sight and sound. Today, advanced automation systems track humidity, airflow, and syrup application rates with sensors and feedback loops, ensuring that every batch meets exacting standards. The result is a product that remains faithful to its original flavor and texture while benefiting from modern advancements in food processing equipment. There is also increasing focus on sustainability in candy production. Many factories now recover and reuse heat from syrup cooking kettles, implement water-saving cleaning systems for coating pans, and work with suppliers to source sugar from more sustainable agricultural operations. Packaging too is being re-evaluated, with lighter materials and improved recyclability being considered for the future. What makes the production of Nerds especially fascinating is the balance between art and science. The process is rooted in classical confectionery techniques that date back centuries, yet it is executed on a scale and with a precision that only modern machinery can achieve. The slight variations in size and shape that give Nerds their charm are not flaws, but deliberate results of the panning process, embraced as part of their identity. The story of Twizzlers begins long before the candy reaches the factory floor. As with many mass-produced confections, the foundation is in the sourcing of high-quality raw materials. The primary ingredient is refined wheat flour, which gives Twizzlers their chewy, slightly bread-like texture. This flour arrives at the plant in bulk tanker trucks and is stored in towering silos that protect it from moisture and contaminants. From here, it is gravity-fed or pneumatically conveyed through sealed pipes to the mixing area. Alongside flour, the recipe calls for corn syrup, which provides sweetness, binding power, and flexibility, as well as sugar, which boosts flavor and adds structure. Vegetable oil, often in the form of soybean or palm oil, contributes to the mouthfeel, while food-grade colors and flavorings give Twizzlers their signature appearance and taste. Every ingredient undergoes rigorous inspection in the quality control laboratory before it can be released to production. Flour samples are checked for protein content and moisture levels. Sugar is screened for crystal uniformity, and corn syrup is tested for viscosity and purity. Liquid flavors and colors are reviewed for consistency against reference standards. Once approved, ingredients move into the blending stage, where the transformation from raw material to candy dough begins. The mixing process takes place in large stainless steel horizontal mixers fitted with heavy-duty paddles or spiral blades. The operation starts with a precise ratio of flour and sugar being combined, followed by the gradual addition of corn syrup and water. These mixers operate under controlled speeds to ensure the dough develops evenly without excessive heat buildup. Oil is incorporated next, coating the flour particles and contributing to the dough's smooth, pliable consistency. Throughout mixing, operators monitor temperature and dough texture, making small adjustments to moisture content if necessary. In many plants, this step is partially automated, with sensors tracking torque resistance in the mixer to determine when the dough has reached the ideal elasticity. Once mixed, the candy dough is transferred to the extrusion line. This is the stage where Twizzlers take on their famous twisted rope form. The dough is fed into a large extruder, essentially a high-powered screw press that forces the material through a specially designed die. The screw inside the extruder rotates at a controlled speed, kneading and pushing the dough forward while maintaining an even temperature to prevent premature setting. At the end of the barrel, the die features multiple openings shaped to produce the exact cross-section of a Twizzler rope. For the classic variety, the die includes ridged channels that create the candy's spiral grooves. As the dough emerges from the die, it is still warm and soft, making it easy to shape but vulnerable to deformation. To preserve the precise geometry, the extruded ropes immediately enter a cooling conveyor, a long belt that passes through a tunnel where chilled, dehumidified air circulates. This step lowers the candy's temperature and sets the outer surface while maintaining a chewy interior. The speed of the conveyor is carefully calibrated so that cooling is uniform along the rope's entire length. An interesting detail of Twizzlers' production is that the twist in each rope is not solely a result of the die design. The conveyor belt itself may be equipped with rollers that gently rotate the ropes as they move forward, enhancing the spiral effect. The amount of twist is a delicate balance. Too much rotation can weaken the structure and cause breakage, while too little results in a less distinctive look. After cooling, the ropes are ready to be cut to size. Cutting is performed by high-speed guillotine blades or rotary knives synchronized with the conveyor movement to avoid crushing the candy. For standard snack-sized Twizzlers, lengths are typically between 6 and 8 inches, but the same line can be adjusted to produce miniature bites or extra long versions. The cut pieces now move towards the packaging area, but before they are boxed or bagged, they undergo inspection. Quality control technicians pull samples from the line to check twist uniformity, diameter, weight, and surface texture. The moisture content is measured to ensure the candy retains its chewiness during storage. Flavor is also evaluated by trained sensory panels who compare each batch to established taste profiles. Packaging Twizzlers is a study in efficiency. Depending on the product format, they may be wrapped in flexible plastic film, placed in cardboard trays, or sealed in resealable pouches. The packaging machinery begins with an in-feed system that gently aligns the ropes into uniform stacks. These stacks are then transferred into forming tubes where the plastic film is drawn around them. sealed along the edge with heat and cut into individual packs. Heat seal jaws close the ends to lock in freshness and protect the candy from moisture and oxygen. Lot codes, manufacturing dates, and product identifiers are printed directly onto the packaging by inkjet or thermal printers, ensuring traceability for every unit. Sealed packages are collected onto a takeaway conveyor and then collated into larger cartons for shipping. These cartons are stacked on pallets by robotic palletizers, which arrange the boxes in stable patterns and wrap them in stretch film to secure the load. From here, the pallets are moved to the warehouse, a temperature-controlled environment designed to maintain product quality. Although Twizzlers are relatively stable due to their low moisture and high sugar content, excessive heat can cause surface stickiness or deformation, so storage temperatures are carefully regulated. The finished products are then shipped to distribution centers, retail outlets, and export markets. Behind all of this is a network of automation systems and process controls that keep production running smoothly. Modern Twizzlers plants rely on programmable logic controllers to coordinate mixer cycles, extrusion pressures, conveyor speeds, and packaging rates. These systems integrate with quality control data, enabling operators to adjust parameters in real time if a batch shows signs of deviation from the standard. The flavoring of Twizzlers deserves special mention. While the classic strawberry variety is the most famous, the process allows for a wide range of flavors, from cherry to chocolate to licorice. In each case, the flavor oils are blended into the dough at the mixing stage to ensure even distribution. The choice of flavor affects other parameters as well. For example, chocolate varieties may require a slightly different extrusion temperature due to the fat content in cocoa powder, while licorice varieties may use molasses or anise oil that alter dough handling characteristics. Over the years, Twizzlers production has been refined not only for efficiency, but also for consistency. Early methods required more manual handling, with operators guiding ropes off the extruder and cutting them by hand. Today's operations are highly automated, with minimal direct contact between workers and the product. This not only improves hygiene, but also allows for higher output with fewer defects. Sustainability is becoming a greater focus in candy manufacturing as well. Plants are investing in closed-loop water systems for cooling conveyors, energy-efficient ovens for any heat treatment steps, and waste reduction programs that recycle off-spec candy back into the mix when feasible. Packaging materials are also being evaluated for recyclability, with thinner films and plant-based plastics under consideration. What makes the Twizzlers process so fascinating is the combination of bakery-like dough handling with candy-making sweetness. The extrusion technology is similar to that used in pasta production, yet the ingredients and post-extrusion handling are firmly rooted in confectionery science. It is a hybrid process that demands both mechanical precision and an understanding of how sugars, starches, and fats interact under heat and pressure. When you pick up a pack of Twizzlers, you are holding the result of careful ingredient selection, finely tuned mixing and extrusion, precise cooling and twisting, and airtight packaging. Each rope is the product of countless micro adjustments in speed, temperature, and formulation that ensure the candy's texture, flavor, and appearance are exactly as consumers expect. The story of a Haribo gummy begins with the ingredients, each of which is selected for quality and consistency. At the heart of the recipe is gelatin, a protein derived from collagen that gives the candy its characteristic elastic texture. This gelatin arrives at the factory in dry, granulated form and must be carefully hydrated before use. Alongside gelatin, the formulation includes glucose syrup, often produced from wheat or cornstarch, which provides body, prevents crystallization, and contributes to the chewiness. Sugar is another mainstay, giving sweetness and structural integrity. Additional ingredients include citric acid for tartness, natural and artificial flavorings for each variety, and food-safe colorants to create the rainbow of hues that define Haribo's product line. Every batch of ingredients undergoes rigorous testing in a quality control laboratory before it reaches the main production floor. Gelatin is checked for bloom strength, which determines the firmness of the finished candy. Glucose syrup is tested for solids content and viscosity, ensuring it will flow and set properly in the cooking process. Flavor and color concentrates are measured for potency and compared against established standards. Only when the raw materials pass inspection are they released to the production team. The first major step in making Haribo gummies is the cooking process. This begins in large stainless steel vessels called dissolvers or cooking kettles. Here, sugar, glucose syrup, and water are combined and heated under controlled conditions. The heating process brings the mixture to a high temperature, often in the range of 110 to 140 degrees Celsius, allowing the sugars to dissolve completely and the syrup to thicken. Once the sugar syrup reaches the correct density, pre-soaked gelatin is added. The gelatin is never boiled, as high temperatures would damage its gelling properties. Instead, it is stirred in gently once the syrup has cooled to a safe range, typically between 80 and 90 degrees Celsius. At this point, flavorings, acids, and colors are added. For gummy bears, this might include lemon, orange, raspberry, apple, and strawberry flavor profiles, each paired with a corresponding color. The additives are metered in with precision pumps to ensure every batch is consistent in both taste and appearance. Stirring must be thorough but gentle to avoid incorporating excess air bubbles, which could mar the candy's surface. Once the mixture is fully blended, it is ready to be formed into shapes. This is where Haribo's distinctive starch molding process comes into play. The company uses a method called the Mogul system, an automated production line that allows liquid candy to be deposited into detailed molds with incredible precision. The process begins with large trays filled with a fine, dry cornstarch powder. This starch serves two purposes. It prevents the sticky candy from clinging to the trays, and it helps wick away excess moisture during the setting stage. Each tray passes through a stamping unit where metal dies press the shape of the candy into the starch. Tiny, bare outlines, cola bottle profiles, or whatever form is being produced. The impressions are crisp and exact, ready to receive the warm, liquid mixture. From the cooking kettles, the candy syrup is pumped through heated pipelines to a series of depositor nozzles. These nozzles align perfectly with the starch impressions and release measured amounts of syrup into each cavity. The depositor can switch flavors and colors quickly, allowing for multiple varieties to be produced on the same line with minimal downtime. Once deposited, the trays of liquid candy are conveyed into a long, climate-controlled curing room. Here, they rest for 12 to 72 hours, depending on the recipe, temperature, and humidity. During this time, the gelatin network fully sets, giving the candy its final chewy texture, while the starch continues to absorb surface moisture. The curing rooms are kept at specific humidity levels to prevent the candies from drying out too much or becoming sticky. When curing is complete, the trays move to the demolding stage. The gummy shapes are gently lifted from the starch, which is recovered, dried, and sieved for reuse in future molding. Any excess starch clinging to the candies is removed through a combination of mechanical shaking and soft air jets. The gummies, now fully formed, have a matte appearance and a slightly tacky feel at this stage. To give them the glossy finish consumers recognize, the candies are transferred to large rotating drums called glazing pans. Inside, they are tumbled with a thin coating of food-grade waxes such as carnauba or beeswax, along with oils that enhance shine and prevent sticking. The glazing process is quick but crucial, as it also provides a protective barrier against moisture changes during storage. With their appearance perfected, the gummies proceed to the packaging area. Here, high-speed conveyors feed them into multi-head weighers, machines equipped with multiple hoppers that dispense exact amounts to achieve the target package weight. The candies are dropped into pre-formed bags or into the forming tubes of vertical form-fill-seal machines. These machines create a bag from a continuous roll of printed film. Seal the bottom, fill it with the candy, then seal the top in one continuous motion. For variety packs, sophisticated sorting systems group different gummy shapes and flavors in precise ratios before they reach the weighing step. This ensures that every bag contains the intended assortment. Packaging films are chosen for their barrier properties, keeping the gummies fresh while displaying bright branding. Each bag receives a lot code and best before date for traceability, then passes through metal detection equipment as a final safety measure. The finished bags are gathered into cartons, stacked onto pallets, and wrapped in stretch film to stabilize them for shipping. Pallets are moved to temperature-controlled storage areas until they are loaded onto trucks bound for distribution centers and retailers around the world. Throughout the entire process, quality control remains a constant presence. Samples from each batch are taken at multiple points, from syrup cooking to molding, curing, and packaging, to ensure that every aspect meets Haribo's specifications. Technicians test texture with penetrometers to confirm the perfect chew, measure pH to monitor acidity, and use colorimeters to verify hue accuracy. Flavor panels taste test samples to ensure the product matches established sensory profiles. The production of Haribo gummies has evolved significantly over the decades. Early batches were made by hand in small copper kettles and poured into starch molds one tray at a time. Today's lines can produce hundreds of thousands of pieces per hour, with computerized systems controlling every variable. Yet the core principles remain the same: quality ingredients, precise cooking, careful molding, and patient curing. There is also a growing emphasis on sustainability within Haribo's operations. Many plants now use energy recovery systems to capture heat from cooking processes, recycle starch indefinitely, and source gelatin and sugar from more sustainable supply chains. Efforts to reduce packaging weight and increase recyclability are also underway, ensuring that the joy of gummy bears has a smaller environmental footprint. What makes Haribo's process fascinating is the blend of old-world confectionery craftsmanship and high-tech automation. The mogul molding system, for instance, is an industry standard, yet it still relies on principles that candy makers have used for over a century. The long curing time is a reminder that some aspects of candy making simply cannot be rushed if the desired texture is to be achieved. By the time a bag of Haribo gummies reaches the shelf, it has undergone a transformation from raw sugar, syrup, and gelatin into a perfectly shaped, flavorful, and brightly colored treat. Behind each piece is a network of ingredient sourcing, controlled cooking, precision molding, and patient curing, all supported by layers of quality control and packaging expertise. It all begins, unsurprisingly, with flour. Krispy Kreme uses a proprietary blend of enriched wheat flour, one formulated specifically for its lightness, protein balance, and ability to yield that signature fluffy bite. The flour is sourced from select mills that maintain tight quality control standards, ensuring the particle size, protein content, and gluten strength all fall within strict tolerances. Once delivered to the facility, the flour is stored in stainless steel silos under controlled temperature and humidity, preventing clumping and spoilage. Next, there's yeast, the biological engine behind the dough's rise. Krispy Kreme uses a commercial strain of baker's yeast known for its rapid activation, consistent fermentation profile, and neutral flavor. The yeast is usually delivered in refrigerated blocks or vacuum-sealed pouches to ensure maximum viability. Alongside the yeast, the other raw ingredients include non-fat dry milk powder, high-stability vegetable shortening, dextrose, salt, and water. Each of these ingredients plays a crucial role in shaping the final taste and texture of the donut. The shortening provides mouthfeel and moisture retention, while the dry milk lends a creamy undertone and enhances browning during frying. In the mixing phase, the ingredients are loaded into a spiral or planetary industrial mixer. The water is typically warmed to around 95 to 105 degrees Celsius before being introduced to activate the yeast. The mixer operates on a timed cycle, first gently combining the dry and wet components, then increasing speed to develop gluten and build dough structure. The dough is mixed until it achieves a smooth, elastic consistency with careful monitoring of temperature and hydration levels. If the dough becomes too warm, it risks overproofing, too cold, and fermentation is delayed. Sensors in the mixing bowl monitor the dough's internal temperature, moisture content, and even CO2 output to ensure consistency. Once the dough is formed, it enters the bulk fermentation phase. Giant stainless steel troughs, called dough rests, hold the dough as it ferments for the first time. During this period, the yeast metabolizes sugars and starches, producing carbon dioxide and ethanol. This expands the dough and begins developing its light, spongy structure. Krispy Kreme controls this step precisely, maintaining a temperature of around 80 degrees and 85% relative humidity in the proofing room. The dough rests here for approximately 30 to 40 minutes, depending on the batch size and ambient conditions. After bulk fermentation, the dough is transferred to a sheeting system. This is where things start to get visually impressive. The dough is rolled and flattened by calibrated rollers until it reaches a uniform thickness, typically between 10 to 12 millimeters. From here, it enters the cutting stage. A rotary die cutter stamps out perfect donut rings and holes in a continuous, automated process. The cutting dies are precision machined from stainless steel to ensure sharp, clean cuts and minimal dough waste. Any scrap dough is immediately collected by conveyors and reintroduced into the mixing system for reuse. Each donut ring now travels along a conveyor to the second proofing chamber, essentially a gigantic, climate-controlled cabinet lined with slow-moving racks. Inside, the donuts undergo their final proof, where they double in size due to continued yeast activity. The environment here is tightly regulated, around 90 degrees here and nearly 85% humidity. This proofing process typically lasts 30 minutes, but sensors embedded in the chamber walls adjust for ambient shifts in temperature or humidity, ensuring each donut achieves the perfect rise. Now comes one of the most mesmerizing parts of the process, the fry line. The fully proofed donuts are gently deposited into a continuous flow fryer using an overhead lifting mechanism that preserves their delicate structure. The frying oil, usually a high stability palm or soybean blend, is maintained at a precise temperature of approximately 365 degrees. Each donut floats along the surface, first frying one side, then automatically flipping at the midpoint using a mechanical turner. This results in the even golden brown exterior Krispy Kreme is known for, with a pale proof line around the center indicating proper fermentation. The frying process takes just under a minute per side, and the timing is crucial. Over-frying results in a dense, oily product. Under-frying leaves it doughy and structurally unsound. Oil filtration systems continuously clean and circulate the frying oil, removing carbonized particles and extending the oil's life while maintaining food safety. Once the donuts exit the fryer, they move onto a draining conveyor where excess oil drips away. The donuts are now fully cooked, but they're still bare until they pass through the glaze waterfall. This is the stage most visitors at Krispy Kreme stores eagerly watch through the viewing window. The glaze itself is a proprietary blend of confectioner's sugar, water, and stabilizers, mixed in large heated vats to maintain fluidity. It's heated to a precise temperature to ensure it flows evenly over the donuts without soaking them. As the donuts travel beneath the waterfall, a curtain of glaze coats their entire surface in one smooth motion. The donuts continue to move along the belt for several feet to allow the glaze to set. During this time, cooling fans blow across the surface to speed up the crystallization process, giving the glaze its characteristic sheen and snap. At this stage, the original glazed donuts are complete, But not all donuts stop here. Many are diverted down alternate lines for filling, topping, or decoration. Filled varieties like custard, jelly, or cream-filled donuts are processed using pneumatic injection stations. The donuts are gripped and punctured automatically, and then a precise quantity of filling is injected into each center using calibrated nozzles. Topping lines include various enrobing stations for chocolate dips, icing drizzles, and even cookie crumb coatings, depending on the product line. Once decorated, the donuts pass through a final quality control checkpoint. Here, high-speed cameras, sensors, and human inspectors work in tandem to identify deformities, glaze coverage issues, or structural flaws. Any donut that doesn't meet the company's stringent standards is diverted and discarded or sent for animal feed, depending on local regulations. Now comes the packaging process. Original glazed donuts are usually arranged by robotic arms into branded trays or boxes, depending on the sales channel, whether destined for in-store display, grocery retail, or food service distribution. Boxes are barcoded, date-stamped, and sealed automatically. For freshness, Krispy Kreme relies on just-in-time manufacturing. Many facilities bake and ship multiple times per day, with some outlets even co-located within the production plant itself to reduce handling and delay. For external distribution, the boxed donuts are loaded into climate-controlled trucks equipped with racking systems that prevent damage during transit. These trucks make scheduled routes to retail locations, grocery partners, and kiosk outlets, often arriving just hours after the donuts were made. Once on site, employees stock the shelves or display racks, ensuring the donuts are sold within their optimal freshness window, typically less than 24 hours. Meanwhile, any donuts not sold by the end of the day are generally removed to preserve Krispy Kreme's reputation for freshness. In some regions, unsold inventory is donated to food banks or repurposed, while others adhere to strict disposal policies. Throughout this entire process, automation and precision engineering play a central role. From programmable logic controllers managing the mixing and proofing cycles, to machine vision systems inspecting glaze coverage, every step is optimized for consistency, safety, and speed. The machinery involved is custom designed, often proprietary, and requires teams of trained technicians to maintain. Clean-in-place systems are installed throughout the facility to sanitize pipes, mixers, glaze troughs, and conveyors between production runs. This minimizes downtime while ensuring compliance with food safety regulations. Every aspect, from microbial swab testing to allergen control and traceability, is monitored via centralized software platforms, which can track each batch of donuts from flour silo to store shelf. The story of every M&M starts with one essential component: chocolate. The heart of a standard M&M is a solid drop of milk chocolate, though other varieties, like peanut, almond, crispy, pretzel, or peanut butter, feature different cores. But regardless of the variety, the production begins in the chocolate refining department, where raw ingredients such as cocoa liquor, cocoa butter, sugar, and milk solids are blended to make a smooth, consistent chocolate base. The chocolate used in M&Ms is tailored for firmness and melt resistance, specifically engineered to maintain its structure during the coating process. Large stainless steel tanks are used to melt and hold the chocolate at controlled temperatures. Automated valves and mixers regulate temperature, viscosity, and flow characteristics. Chocolate destined for M&M production must be carefully refined to reduce particle size, usually to around 20 microns. This is done in multiple stages using equipment like ball mills, roller refiners, and conchas. These machines apply friction, pressure, and shear force to break down the solid particles until the chocolate achieves its desired mouthfeel. Once refined, the chocolate is pumped to depositors, automated nozzles that precisely dispense the liquid chocolate into molds or droplet-forming equipment. For the classic M&Ms, the chocolate is dropped onto a cool, rotating belt in small, round portions, forming button-shaped discs. These droplets are cooled rapidly using chilled air tunnels to harden them before further processing. The cooled chocolate centers are then collected and sent to the coating drums. These are large rotating pans, sometimes referred to as dragees pans or coating kettles, where the hard candy shell is gradually built around the chocolate core. This is the heart of the M&M production process and one of the most visually striking steps in the factory. The coating process is a slow and incremental buildup, achieved by spraying a fine mist of sugar syrup onto the tumbling chocolate centers, then drying and hardening that layer before repeating the cycle. Each coating drum can hold hundreds of thousands of chocolate centers at once. As the drum rotates, a fine spray of syrup, consisting mainly of sugar and water with optional corn syrup, is applied in short bursts. Warm air is then blown into the drum to dry the layer, allowing the sugar to crystallize into a thin, hard shell. This cycle is repeated dozens of times, each time adding a microscopically thin layer to build up the final shell thickness. Over time, this layering transforms the centers from soft chocolate buttons to perfectly round, hard-shelled candies. During this stage, technicians monitor coating uniformity, size consistency, and drying times using high-speed cameras and inline sensors. If the temperature or humidity in the coating room deviates too far from spec, it can ruin an entire batch, leading to shell cracking or poor adhesion. Once the desired shell thickness is achieved, the M&Ms are polished to give them their signature shine. This is done by adding polishing agents, such as carnauba wax or beeswax, to the coating drum in very small amounts. These natural food-grade waxes help create a glossy finish that not only enhances visual appeal, but also helps prevent sticking and moisture absorption during storage. The polishing phase takes less time than coating, but must be precisely timed to avoid over-waxing, which can result in a greasy or smeared appearance. The next step is color application, which may seem simple, but is, in fact, a carefully controlled phase. M&Ms come in a variety of colors, typically red, orange, yellow, green, blue, and brown. The color coding is applied using a sugar-based dye solution, sprayed in another round of layering inside rotating pans. Each batch is divided according to how many of each color are required. Food-grade colorants are mixed with water and a binding agent to ensure even adherence to the existing shell. After the colorant is applied, warm air is used to dry the layer, and another wax polish may be added to lock in the color and maintain shine. The factory uses precise batch tracking and automated scheduling software to ensure the correct number of each color is produced. For example, if red accounts for 20% of a standard bag's color distribution, the system ensures exactly that percentage is created during the run. This attention to detail keeps the consumer experience consistent across bags, boxes, and geographic regions. After color coding, the candies proceed to the printing station, where the iconic M is stamped on each piece. This is accomplished using high-speed, food-safe ink printers. The M&Ms are gently vibrated into a single layer on a moving conveyor belt that aligns them properly for stamping. The white edible ink is applied using a flexographic or offset stamping mechanism that imprints the M logo without damaging the candy surface. To ensure accuracy, machine vision systems monitor the printing in real time, checking for clarity, alignment, and completeness. Any candies that are misprinted or blank may be removed by pneumatic air jets and diverted for recycling or reprocessing. Now the M&Ms are ready for packaging. This phase of production involves a combination of robotics, weight-checking systems, and packaging machinery that operates at astonishing speeds. The candies are directed into vertical form-fill-seal machines or horizontal flow wrappers, depending on the packaging format. Multi-head weighers dispense precise quantities of M&Ms into each bag or pouch, ensuring weight compliance to legal standards. The packaging film is heat-sealed to form a tamper-evident, airtight barrier that preserves freshness and extends shelf life. For bulk formats, such as large tubs, party-sized bags, or vending packs, the process is slightly different but still highly automated. The machines are programmed to handle various product sizes, materials, and pack types without compromising accuracy. Barcodes, expiration dates, and lot numbers are printed onto each package to allow for traceability. Once packaged, the products are conveyed to case packing robots, which group them into cartons or boxes for shipping. These cases are then sealed, palletized by robotic arms, and shrink-wrapped for transport. Pallets are stored temporarily in climate-controlled warehouses before being loaded onto distribution trucks that carry them to retail centers, convenience stores, vending machine suppliers, and international shipping hubs. Throughout the entire process, food safety and quality control are paramount. The factory floor is governed by strict hygiene protocols. Employees are required to wear sanitary gear, and the equipment is sanitized regularly using automated clean-in-place systems. Random sampling is conducted at every critical control point, from chocolate refining to shell thickness to final packaging. Laboratory testing checks for microbial contamination, allergen presence, and chemical composition. Quality assurance teams also perform taste tests, structural integrity tests, and heat resistance trials to ensure the product meets Mars Inc.'s global standards. In the case of peanut or almond M&Ms, the process is similar but begins with nut preparation. Peanuts, for instance, are roasted in-house to develop their flavor and reduce microbial load. They are then cooled, sorted by size, and coated in a preliminary layer of chocolate before undergoing the same sugar shell layering process. Their irregular shape requires adjustments to coating speed and rotation patterns to ensure even coverage. The engineering behind M&M production is not only a marvel of food science, but also a study in high-speed manufacturing. Thousands of M&Ms can be produced every minute, yet each one must look and taste exactly the same. This requires the coordination of multiple disciplines: mechanical engineering, chemistry, automation, logistics, and sensory evaluation. The process begins not with whole potatoes, but with dehydrated potato flakes and potato starch. These form the base of the Pringles dough. The flakes are manufactured off-site through a separate drying process where peeled, cooked potatoes are mashed and then passed through drum dryers to remove water, creating thin, crisp sheets of dried potato. These are ground into fine granules and delivered to Pringles production facilities in bulk quantities, stored in climate-controlled silos to maintain moisture levels and prevent clumping. To this potato base, manufacturers add a precise blend of rice flour, corn flour, and wheat starch. This multi-starch formula gives Pringles their distinctive light, yet durable crunch, firmer than a classic chip, but less dense than a cracker. Each ingredient is selected for its functional properties. Rice flour contributes to lightness and reduces oil absorption. Corn flour provides structure and contributes to the crisp texture. Wheat starch acts as a binding agent and helps form the dough into a cohesive sheet. Inside the factory, these dry ingredients are metered into high-capacity industrial mixers. Water is added gradually, and the mixture is agitated until a cohesive dough forms. The consistency of the dough is critical. It must be pliable enough to be rolled and shaped, yet stiff enough to hold its form during frying. Too much water would cause the crisps to bubble and deform. Too little, and they would crack or crumble during processing. After mixing, the dough is conveyed onto a series of steel rollers in a sheeting machine. These rollers press the dough into a continuous, thin sheet, typically about 0.7 to 1 millimeter thick. The uniformity of this sheet is crucial, as even slight thickness variations can affect how the chips fry, blister, and brown. Advanced sensors mounted near the rollers continuously monitor sheet thickness, feeding data to the control system, which makes micro adjustments in real time. Next, the sheeted dough passes under a rotary die cutter. This is a cylindrical cutter with thousands of identically shaped molds engraved into its surface. As the sheet moves beneath it, the die cuts out dozens of curved oval crisps at a time, each one precisely measured to match Pringles' iconic dimensions, around 6.5 centimeters long and 5.5 centimeters wide, shaped with a unique double-curved profile known as a hyperbolic paraboloid. This mathematical shape isn't just aesthetic, it offers stackability, strength, and an audible crunch due to its uniform stress distribution. The dough scrap that remains between the cutouts is immediately separated and returned to the beginning of the process. Conveyor belts collect and transport the unused dough back to the mixer, where it is reincorporated into fresh dough. This closed-loop system minimizes waste and ensures efficiency in ingredient usage. Once cut, the raw crisps are gently lifted from the sheet using suction cups or air jets and placed onto a moving metal belt composed of dozens of concave molds. Each mold perfectly matches the chip's final saddle shape. This belt then moves the raw crisps into the fryer, an enormous stainless steel bath filled with hot vegetable oil, maintained at a consistent temperature of around 170 to 180 degrees. The crisps are submerged for approximately 11 seconds, long enough to remove moisture and induce a Maillard reaction, giving them their light golden brown hue and toasty flavor. Unlike traditional deep-fried potato slices that can curl, bend, or form bubbles, the Pringles molds maintain each crisp's structure during frying. Because the crisps are uniformly thin and precisely shaped, they fry evenly with no dark spots or oil saturation. Excess oil is quickly removed as the crisps exit the fryer and pass over a series of vibrating conveyors and air knives, high-pressure jets that blow away any surface oil or crumbs. At this point, the freshly fried crisps are hot, dry, and unseasoned. They move into the seasoning tunnel, a long, rotating drum equipped with sprinklers or spray nozzles. Here, flavor powders, ranging from classic original to sour cream and onion, cheddar cheese, or barbecue, are evenly applied as the crisps tumble and rotate. The flavor powders are formulated to stick to the crisp's surface via residual oil left from frying. In some varieties, additional ingredients such as powdered cheese or dehydrated vegetables are included in the seasoning blends. To prevent flavor loss and preserve freshness, the seasoned crisps are quickly cooled using forced air systems before entering the packaging phase. This cooling is critical. If the crisps are too warm, condensation can form inside the package, leading to soggy chips and microbial risk. Once cooled, they are conveyed to the stacking and canning line. This is where another defining feature of Pringles becomes prominent: their tubular canister. The stacking machine uses a system of synchronized mechanical arms, optical sensors, and robotic paddles to stack crisps one by one into perfectly aligned columns. This process is remarkably fast and precise. A sensor verifies each crisp's shape and orientation before it's inserted into the growing stack. Once a full stack reaches the correct height, typically around 80 to 100 crisps, depending on the packaging size, it is inserted vertically into a cardboard can that's been pre-formed and lined with a metallized film to prevent oil seepage and moisture intrusion. Each can is equipped with a plastic bottom, which is ultrasonically welded or heat sealed in place before filling. After the crisps are inserted, a foil lid is applied and hermetically sealed using induction heat or pressure bonding to ensure an airtight closure. A plastic snap-on cap is then placed on top, providing resealability for consumer convenience. The filled cans are then labeled and date-coded. Each can receives a printed batch number and expiration date to ensure traceability throughout the distribution chain. Vision inspection systems scan each can to ensure it is filled to the correct level, sealed properly, and free of any external defects like dents or mislabeling. Cans are grouped into multi-packs or cartons by robotic arms and placed on pallets for storage or shipment. Depending on demand and product line complexity, different varieties of Pringles may be produced in separate production runs on the same line, requiring quick and thorough cleanouts between batches to prevent flavor cross-contamination. From here, Pringles are shipped to distribution centers, retailers, and convenience stores across the globe. Thanks to the uniform shape and rigid packaging, they travel exceptionally well, with minimal breakage compared to traditional bagged chips. This durability, coupled with the brand's distinct identity, has made Pringles a staple in global snack markets. Sanitation and quality control are central throughout the process. Each stage of production, from dough mixing to final packaging, is monitored by automated control systems and human operators. Random samples are collected for lab analysis to check moisture levels, oil content, seasoning distribution, and texture. Microbial testing ensures no contamination occurs during handling. Metal detectors and X-ray machines inspect each can before shipping to catch any foreign objects that may have entered the line. Allergen controls are strictly enforced, particularly when switching between varieties like original and cheddar cheese. In addition to ensuring food safety, the factory design and equipment layout support continuous cleaning. Many machines feature clean-in-place systems that pumps sanitizing fluids through the equipment without requiring disassembly. Air filtration systems and positive pressure rooms minimize the risk of dust and airborne contaminants affecting product quality. Beyond the manufacturing floor, the creation of new Pringles flavors and formats involves food scientists and R&D specialists who develop seasoning blends, test mouthfeel, and conduct sensory panels with trained tasters. Innovations like Pringles Wavy or Pringles Scorchin follow the same base process, with minor adjustments in dough formulation or seasoning protocols. Despite their high-tech origin, Pringles still deliver a simple satisfaction, a crisp, flavorful bite that feels familiar and fun. But behind that enjoyment is a complex dance of precision equipment, mathematical shaping, and carefully designed formulations. From powdered potatoes to perfectly stacked crisps, every Pringle is a product not just of flavor, but of industrial ingenuity, a testament to how food science can transform something as humble as a potato into a globally recognized snack. The process for Reese's Peanut Butter Cups begins with the sourcing of high-quality raw peanuts, which form the core of the filling. These peanuts are typically sourced from farms in the southeastern United States, particularly Georgia, Alabama, and the Carolinas, where the climate and soil are ideal for peanut cultivation. Once harvested, the peanuts undergo initial cleaning, shelling, and sorting at the agricultural level before being shipped in bulk to the Reese's production facility. Quality control teams inspect every shipment, screening for mold, aflatoxins, and other contaminants. Peanuts are often tested for size, moisture content, and oil composition to ensure batch consistency. Upon arrival at the factory, the peanuts are conveyed to large storage silos. From here, the process of transforming raw peanuts into the signature Reese's filling begins. The peanuts are first roasted in large-scale industrial roasters, long horizontal drums heated by indirect gas-fired flames. These rotating drums tumble the peanuts slowly, ensuring even roasting. Temperature and humidity are closely monitored throughout the roast cycle, typically maintained around 320 degrees Celsius for about 30 to 40 minutes, depending on the peanut variety and moisture content. Once roasted, the peanuts are quickly cooled using forced air cooling tunnels to halt further cooking. The skins are then removed using a process known as blanching. In mechanical blanches, peanuts are agitated against rough surfaces or rubber belts that strip away the thin, papery skins. A series of air jets and vibrating sieves separate the skins from the now blanched nuts. At this point, the peanuts are ready to be ground. In most candy factories, this process takes place in two distinct phases. First, a coarse grind reduces the peanuts into a crumbly paste. Then, a finer grinding process, often using high-speed colloid mills or stone rollers, produces a smoother texture. However, unlike creamy commercial peanut butters designed for spreads, Reese's peanut butter filling maintains a slightly gritty texture on purpose. This signature mouthfeel is the result of limiting the duration of the fine grind and carefully controlling moisture levels. The ground peanuts are blended with additional ingredients, including sugar, dextrose, salt, hydrogenated vegetable oils, and sometimes a small amount of molasses or corn syrup solids. This mixture is prepared in large industrial mixing tanks equipped with powerful paddle agitators that ensure even incorporation. The blending process is closely monitored for temperature, viscosity, and particle size distribution, which directly affect the final texture and handling characteristics. The resulting peanut butter filling is slightly crumbly, yet cohesive, designed to hold its shape when formed, but melt smoothly in the mouth. While the peanut butter filling is being prepared, another part of the factory is busy tempering chocolate. Reese's Peanut Butter Cups use a custom milk chocolate formulation that includes cocoa solids, cocoa butter, milk fat, sugar, lecithin, and vanillin. These ingredients are pre-blended and then passed through conching machines, large vats where granite rollers continuously knead the chocolate for hours at elevated temperatures. Conching improves texture and flavor by breaking down particles and promoting the development of complex chocolate notes. After conching, the chocolate is sent to tempering units, which precisely heat and cool the chocolate in a controlled sequence to encourage the formation of stable cocoa butter crystals. Proper tempering is critical to achieving that characteristic Reese's snap and glossy finish. The chocolate must be maintained at a working temperature of approximately 88 degrees to 90 degrees for milk chocolate, depending on the formulation. Now the production line shifts into high gear with the molding and filling of each peanut butter cup. The factory floor features a long assembly line comprising conveyor belts, servo-driven depositing heads, forming stations, and robotic arms, all synchronized with computer-controlled systems. First, paper cup liners are dispensed from reels and dropped into aluminum or plastic molds that give the peanut butter cup its distinctive ridged edge. These molds are carried forward on the conveyor to the chocolate depositing station. Here, a metered amount of tempered chocolate is deposited into each mold cavity, typically via piston-driven depositors with highly accurate flow control. The molds are then gently vibrated to level the chocolate and remove any trapped air bubbles. A specialized spinning or centrifugal molding mechanism is often used to coat the sides of each liner with chocolate, forming a thin shell that will encase the peanut butter filling. Once the bottom and sides of the shell are set, often using brief passes through cooling tunnels chilled to 40 degrees F, the molds move to the filling station. At this point, the peanut butter mixture is slightly warmed to improve flowability and deposited into the center of the chocolate shell using a second set of depositors. The volume and placement are tightly controlled to ensure the filling does not breach the shell's perimeter, which would compromise product appearance and shelf life. The partially filled molds then travel through another cooling tunnel to partially firm up the filling before the final chocolate cap is added. At the next station, another measured deposit of tempered chocolate is layered on top to fully enclose the peanut butter. Vibratory and centrifugal actions again ensure that the top layer is smooth and fully seals the filling inside. After the top layer is applied, the molds pass through the final cooling tunnel. This tunnel, often more than 30 feet long, gradually lowers the product temperature to about 50 degrees to 60 degrees F, allowing the chocolate to fully crystallize and harden without cracking or bloom. At the end of the tunnel, robotic demolders invert the trays and the solidified Reese's peanut butter cups drop gently onto another conveyor belt, which carries them to the packaging line. Packaging is a critical part of the operation, both for aesthetics and product protection. Individual cups are wrapped in printed foil or plastic film using high-speed flow wrapping machines. These machines align, wrap, heat seal, and cut the packaging material in a continuous motion at speeds of hundreds of units per minute. Sensors and vision systems verify proper alignment, seal integrity, and date coding. Multiple wrapped cups are then grouped into standard pack formats, such as 2-packs, king size, or multi-packs, using pick-and-place robots that transfer the wrapped candies into cardboard sleeves or blister packs. These are then loaded into shipping cartons by automated case packers and sent through weight check stations and metal detectors for final safety assurance. Cartons are sealed, barcoded, and palletized using robotic palletizers that arrange the boxes into stable stacks ready for shipment. The finished pallets are shrink-wrapped for transport and loaded onto refrigerated trucks, if necessary, depending on the season and destination. Distribution centers receive the pallets and coordinate the movement of Reese's products to retail chains, vending machine operators, and wholesale clubs. Shelf life is generally around 6 to 9 months, and climate-controlled storage is crucial to preventing fat bloom or flavor degradation in the chocolate. Inventory is rotated using first-in, first-out logistics to ensure product freshness. Reese's peanut butter cups may seem like a simple treat, but their production involves a complex interplay of food science, automation, engineering, and quality control. Each cup reflects countless micro-adjustments made by operators, engineers, and sensors throughout the line to maintain consistency in taste, texture, and visual appeal. Whether you're biting into a miniature, a king size, or a seasonal shape, the same rigorous standards apply across every variation. The process for Snickers begins long before a single bar is formed. It starts with the procurement of raw ingredients, each of which must meet stringent quality, flavor, and food safety standards. The peanuts used in Snickers are typically sourced from large-scale growers in the United States, particularly Georgia, Texas, and Alabama, where soil composition and climate are well suited to peanut cultivation. Once harvested, the peanuts undergo shelling, drying, and initial quality control before arriving at the candy factory in bulk loads. At the receiving dock, they're sampled and inspected for size uniformity, absence of mold or aflatoxins, and overall freshness. The peanuts are then conveyed to roasting units, large, gas-fired, rotary drum roasters that tumble and cook the nuts evenly. Roasting time and temperature are carefully controlled, often in the range of 300 degrees to 330 degrees, to ensure the development of the characteristic deep nutty flavor and golden color. As the peanuts cool on vibratory trays with forced air, their skins are loosened and removed through mechanical blanching, which typically involves abrasion and suction systems. Once the peanuts are blanched, they are screened again for foreign matter or off-grade pieces before being held in stainless steel hoppers, ready for integration into the bar. While the peanuts are being prepared, another production stream begins with the making of the nougat layer, the foundational component of every Snickers bar. Nougat is a whipped mixture, typically composed of sugar, corn syrup, egg whites, and milk powder. The sugar and corn syrup are first combined in massive stainless steel cooking kettles, where they are heated to a precise temperature, usually around 240 degrees to 250 degrees, to achieve the correct sugar structure and viscosity. This hot syrup is then transferred to continuous mixing tanks where it is combined with whipped egg whites and other dry ingredients. The blending process is highly aerated, giving the nougat its light, spongy texture. The finished nougat is deposited onto a moving conveyor belt lined with parchment or plastic film. It spreads out in a continuous sheet, generally about 1 to 2 inches thick. A series of levelers and rollers ensures uniform height and density across the sheet, which is then cooled slightly as it travels down the line. Once cooled and set, the nougat sheet proceeds to the caramel layering station. Caramel production occurs in its own dedicated section of the plant. A blend of glucose syrup, sucrose, dairy cream, and butter is cooked in open-jacketed kettles or vacuum cookers, where it is continuously stirred to avoid burning and to control the Maillard browning reactions that give caramel its signature flavor. The exact temperature and cooking duration are tightly monitored, typically between 240 degrees Celsius and 260 degrees. As soon as the desired consistency is achieved, firm enough to hold its shape but pliable enough to slice, it is poured or extruded onto the moving nougat sheet. The hot caramel forms a second, cohesive layer atop the nougat. To ensure perfect adhesion and uniform thickness, the bar sheet passes under heated rollers and through spreading nozzles that guide and adjust the caramel's distribution. The line is equipped with infrared sensors and weight check systems that continually monitor thickness and material ratios. Once the caramel has slightly cooled and stabilized, the bar sheet moves toward the peanut application zone. Roasted peanuts are sprinkled onto the warm caramel layer in a controlled shower using vibrating feed trays and metered dispensers. The combination of slightly sticky caramel and downward pressure ensures that most peanuts adhere securely. Excess or misaligned nuts are brushed away by rotating silicone paddles and collected for reuse or reprocessing. The peanuts used here are not only flavor critical, but also provide a distinctive crunch and texture contrast to the softer nougat and caramel. With all three internal layers assembled, nougat, caramel, and peanuts, the composite sheet now travels to the cutting area. Here, guillotine-style knives or rotary blade systems cut the long sheet into bar-length strips, typically around 1 inch wide. These strips are then cross-cut into individual bars, using synchronized high-speed blades. Every bar is now a complete unit, except for the chocolate coating. Before coating, the uncoated bars, often referred to as centers, pass through a quick chilling tunnel to firm up the layers and maintain bar integrity during enrobing. Once firm, the centers are deposited onto a wide enrobing belt that passes through a chocolate waterfall. This enrobing process involves a curtain of tempered milk chocolate cascading down over the moving bars. As the bars move through the curtain, chocolate coats the top and sides. A bottoming plate or chocolate pool beneath the bars coats the underside as well. The chocolate used in Snickers bars is a proprietary blend of milk chocolate ingredients, cocoa butter, cocoa liquor, sugar, milk solids, and emulsifiers. The chocolate is pre-tempered in dedicated machines that heat and cool it through specific curves to ensure stable crystal formation. This tempering is what gives Snickers its glossy finish and prevents fat bloom during storage. The temperature of the chocolate is carefully maintained between 86 degrees Celsius and 90 degrees Celsius throughout the enrobing line. As the chocolate-coated bars exit the enrober, they pass under air jets and vibrating rods known as air knives and vibrators that remove excess chocolate, improve coating uniformity, and give each bar its final shape. The still warm chocolate is soft and easily deformed, so the bars immediately enter a cooling tunnel, which gradually reduces their temperature to around 50 degrees Celsius in a staged fashion. This gradual cooling prevents cracking and ensures that the chocolate shell sets with the correct texture. Once fully cooled, the bars emerge, ready for wrapping. A high-speed automated packaging line awaits, where each bar is individually wrapped using roll-fed film wrappers. These machines synchronize bar movement with film feeding, folding, sealing, and cutting, all in one continuous operation. Heat sealers close the film edges with precision, while inline printers apply best buy dates, lot numbers, and traceability codes. The wrapped bars are then conveyed to a grouping station. Depending on the market, Snickers bars may be packed individually, bundled in twin packs, or combined into multi-unit boxes. Robotic arms sort and orient the wrapped bars, placing them into cartons that are then sealed with hot melt adhesive. The packed cartons are passed through metal detectors and weight verifiers as a final check before palletization. Palletizing robots load the boxes onto standardized pallets, wrapping them tightly in plastic film for protection and stability during shipping. From there, pallets are staged in climate-controlled distribution centers. Temperature and humidity must be carefully controlled, especially in warm climates, to preserve the bar's texture and chocolate integrity. Snickers bars are then distributed to retailers, wholesalers, and vending machine operators worldwide. Shelf life for a standard Snickers bar is generally between 9 and 12 months, assuming proper storage. Mars maintains rigorous quality control protocols, including sampling every batch for flavor consistency, structural integrity, and microbiological safety. Automated inspection systems use vision technology to detect misaligned bars, incomplete coatings, or wrapper defects, automatically removing flawed units from the line. Throughout the plant, hygiene is paramount, with clean-in-place systems for all equipment and strict allergen controls to ensure product safety. What makes Snickers particularly remarkable is how such a complex, multi-layered treat can be produced with such uniformity at an industrial scale. From raw peanuts and liquid caramel to perfectly wrapped bars stacked on pallets, every aspect of production is optimized for speed, precision, and global distribution. Millions of Snickers bars roll off the line each day, each one representing a perfected system of mass food manufacturing. It all begins with cocoa beans for Hershey's chocolate, which are the fundamental raw ingredient in all chocolate. Hershey sources its cocoa beans primarily from West Africa, countries like Côte d'Ivoire and Ghana, where the climate, soil, and traditional farming practices produce high-yield crops with desirable flavor characteristics. Once harvested, the cocoa beans are fermented in banana leaf-lined piles and dried under the sun before being packed in jute bags and shipped across the ocean to Hershey's production facilities in the United States. Upon arrival, the beans are subject to rigorous testing. Random samples from each shipment are roasted and analyzed for aroma, acidity, moisture content, and potential contaminants. Approved beans are stored in large silos, sorted by origin and quality grade. From here, the first major step in the chocolate making process begins roasting. Roasting is not just about cooking the beans, it's a chemical transformation that unlocks the complex flavors hidden within the cocoa nibs. The beans are fed into large, rotating drum roasters or continuous belt roasters and exposed to carefully controlled dry heat at temperatures between 250 degrees and 300 degrees for 20 to 30 minutes. This Maillard reaction develops the chocolate flavor while drying the beans further and loosening the outer shells. The duration and temperature of the roast are adjusted depending on the origin and size of the beans, with constant airflow and humidity control. After roasting, The beans are cooled and sent through cracking machines that break them open, separating the brittle outer shells from the inner nibs. The broken shell pieces are removed through winnowing, a process that uses airflow to lift away the lighter shells, leaving behind clean cocoa nibs. These nibs are the essence of chocolate, rich in cocoa solids and cocoa butter. The nibs are then ground into a thick, gritty paste called chocolate liquor, not to be confused with alcohol. This step is performed in heavy-duty grinding mills, such as stone refiners or steel disc mills, which apply intense pressure and friction. As the nibs break down, their fat melts, turning the mass into a thick, flowing fluid. At this point, the chocolate liquor is still unrefined, with a coarse texture and bitter flavor. For milk chocolate, Hershey adds a blend of sugar, milk ingredients, and sometimes vanilla and lecithin to the chocolate liquor. One of the defining features of Hershey's milk chocolate is its use of fresh fluid milk that is processed in-house. Unlike European chocolates that often use powdered or condensed milk, Hershey pioneered a method of processing fresh milk into milk crumb, a dehydrated mixture of milk solids and sugar, using vacuum cooking and drum drying techniques. This milk crumb, with its slightly tangy cooked flavor, contributes to the uniquely Hershey taste. The chocolate liquor, milk crumb, and sugar are blended in large stainless steel mixing tanks, forming a uniform paste. At this stage, the mixture is still coarse and gritty, unsuitable for final chocolate texture. It must be refined. The refining process involves passing the chocolate mass through a series of roller mills, typically 5-roll refiners that reduce the particle size of the solids to less than 30 microns. The goal is to achieve a silky smooth mouthfeel without any noticeable graininess. Once refined, the chocolate enters the conching phase, one of the most critical steps in flavor development. Conching is a process of continuous mixing, aerating, and heating the chocolate over many hours to improve its taste and texture. Hershey's uses a combination of traditional longitudinal conches and modern rotary conches that knead the chocolate at controlled temperatures, typically between 120 degF and 180 degF. This process helps evaporate undesirable volatile acids, mellow bitter notes, and fully integrate the milk and cocoa flavors. The viscosity and aroma are fine-tuned during this stage through mechanical shearing and time adjustments. Following conching, the chocolate undergoes tempering, a heat treatment process that ensures the final product has a smooth, glossy finish and a crisp snap when broken. Cocoa butter can crystallize in several forms, but only one, known as Form 5, gives chocolate its ideal physical properties. Tempering involves heating the chocolate to about 115 degrees, then cooling it down to around 80 degrees, and finally reheating it slightly to about 88 degrees to promote the formation of stable crystals. This carefully controlled cycle is performed in continuous tempering machines, which maintain consistent temperatures and flow rates. Tempered chocolate is now ready for molding. Hershey's uses high-speed molding lines where liquid chocolate is deposited into polycarbonate molds in precise weights. The molds are vibrated to remove air bubbles and ensure even distribution. For classic bars like the Hershey's Milk Chocolate Bar, the molds are designed with the familiar rectangular break-apart sections embossed with the Hershey name. Once filled, the molds travel through long refrigerated cooling tunnels where the chocolate solidifies into its final form. As the bars cool, they are monitored by temperature sensors and mechanical feelers to ensure proper release. When fully set, the bars are automatically ejected from the molds and conveyed to the wrapping station. Modern wrapping equipment is synchronized with bar output and uses roll-fed film that is printed with the Hershey's branding, ingredients, and expiration codes. Wrappers are folded and sealed using rotary crimpers, and a barcode is applied for tracking. Wrapped bars are then grouped into cartons or display trays using robotic pick-and-place systems and conveyed to the end-of-line packaging area. Here, cases are formed, filled, and sealed before being palletized by automated arms. Each pallet is shrink-wrapped and scanned into inventory, ready for transport to distribution centers across the country and around the world. Throughout the entire process, quality control is a constant presence. Samples are pulled from every batch for testing. Sensory panels evaluate flavor and aroma, while lab technicians measure moisture content, fat percentage, and microbial levels. Machine vision systems inspect each bar for dimensional accuracy and surface defects. Metal detectors and X-ray machines scan for foreign objects, while thermal imaging cameras check for temperature compliance at various stages. Behind the scenes, Hershey's factories are tightly integrated with computerized control systems that track every ingredient, process parameter, and output metric in real time. From ingredient blending to chocolate tempering and bar wrapping, programmable logic controllers and supervisory control and data acquisition systems coordinate the hundreds of motors, valves, conveyors, and sensors that make up the line. These systems not only maximize efficiency and reduce downtime, but also ensure that each bar tastes the same as the one before it. Once packaged and palletized, Hershey's bars enter the post-production logistics chain. Distribution centers maintain climate-controlled storage to preserve chocolate integrity. Trucks are loaded according to first-in, first-out scheduling, and GPS tracking systems ensure timely delivery to retailers, vending machine operators, and wholesalers. Chocolate bars are especially sensitive to heat and humidity, so strict environmental controls are observed throughout transportation and warehousing to prevent melting or bloom. Interestingly, the Hershey flavor that many Americans recognize and even associate with nostalgia is not accidental. It's the result of deliberate formulation choices, particularly in how milk is treated during production. Some analysts believe the signature, slightly sour or tangy flavor found in Hershey's milk chocolate comes from the breakdown of milk fats into butyric acid during controlled lipolysis, an effect that differentiates Hershey's from creamier European chocolates. This flavor profile has become a cultural benchmark in the United States, deeply woven into American food identity. Despite decades of innovation and scaling up, the heart of Hershey's chocolate production still echoes the vision of its founder: to make high-quality milk chocolate affordable and accessible to everyone. With more than a century of history and tens of millions of bars produced annually, Hershey's remains a pioneer in automated food manufacturing, exemplifying the blend of tradition, precision engineering, and industrial food science. From bean to bar, the production of Hershey's chocolate is a story of transformation, driven by technology, but grounded in flavor. The base ingredients include whole milk, cream, sugar, glucose syrup, and sometimes egg yolk for additional texture. These raw materials are sourced from vetted dairy farms and suppliers that comply with stringent quality control measures. Upon arrival at the production facility, the dairy ingredients are immediately transferred into refrigerated holding tanks to maintain their integrity. Here, laboratory technicians perform routine tests for microbiological safety, fat content, and pH levels to ensure the base meets the strict specifications required for premium ice cream. Once the ingredients pass inspection, they're pumped into large stainless steel mixing tanks. These tanks are equipped with high-shear agitators that blend the milk, cream, and sugars into a homogeneous mix. During this phase, emulsifiers and stabilizers, such as mono and diglycerides or guar gum, are added to enhance the creaminess and improve the shelf life of the product. The mixture is continuously agitated and brought to a temperature of approximately 60-70 degrees Celsius to fully dissolve the sugars and emulsify the fats. The next critical step is pasteurization. The liquid mix is sent through a continuous flow pasteurizer, usually a plate heat exchanger, where it is rapidly heated to around 83 degrees Celsius for about 15 seconds. This high temperature, short time pasteurization process ensures the destruction of harmful bacteria while preserving the functional properties of the dairy. Immediately after pasteurization, the mix is flash cooled to below 4 degrees Celsius to minimize microbial growth and is transferred to maturation tanks. In the maturation tanks, which are jacketed vessels with slow-moving agitators, the mix is held at low temperatures for 4 to 12 hours. This resting period allows the emulsifiers and stabilizers to hydrate fully and the fat globules to partially crystallize. Maturation significantly improves the whipping quality of the mix and enhances the texture and body of the final ice cream. With the mix properly matured, it is now ready for freezing. The liquid base is pumped into continuous freezers, which are essentially refrigerated barrel drums equipped with rotating scraper blades. As the mix is pumped through these freezers, it is simultaneously aerated and frozen. The aeration, or overrun, is carefully controlled to maintain Magnum's signature dense texture, with overrun values kept well below standard commercial ice cream. The continuous freezer operates at sub-zero temperatures, rapidly freezing the mix to around -5 degrees Celsius while incorporating microbubbles of air for creaminess. At this semi-frozen stage, the ice cream has reached a soft serve consistency and is now ready for molding. One of the defining features of Magnum bars is their perfectly oval, bar-shaped form. This is achieved using a high-speed rotary molding system. Rows of stainless steel molds, pre-chilled to approximately -30 degrees Celsius, are arranged on a conveyor belt that dips them into a vat of liquid ice cream. As the molds emerge from the bath, the ice cream begins to freeze instantly against the chilled metal surfaces. To ensure a consistent core, the partially filled molds are passed through a hardening tunnel. This tunnel is essentially a blast freezer operating at -40 degrees Celsius or lower, using forced air circulation to rapidly solidify the product. Once hardened, the bars are extracted from the molds using a short burst of warm air or a mechanical press system. Immediately upon demolding, the ice cream bars are affixed to wooden sticks via a precise robotic inserter. These sticks, usually made of sustainably sourced birch or poplar wood, are sterilized and fed into the system through automated dispensers. Now comes one of the most iconic steps in the process: the chocolate enrobing. Magnum's chocolate coating is what sets it apart from most other ice cream bars. The chocolate used is often Belgian in origin and must meet exacting melt and viscosity specifications. It arrives at the factory in solid form and is melted down in jacketed tanks fitted with stirrers that maintain a constant, uniform temperature, typically around 40-45 degrees Celsius, to ensure a smooth flow. The hardened ice cream bars are conveyed toward the enrobing station, where they pass over a curtain of liquid chocolate. Each bar is dipped or showered with the molten coating using a carefully calibrated nozzle system. The chocolate immediately begins to solidify upon contact with the supercooled surface of the ice cream, forming the signature crack when bitten into. To achieve a uniform coating thickness, the enrobing line is equipped with vibration tables and air knives that remove excess chocolate without disturbing the integrity of the shell. Depending on the variant, classic, almond, white, or one of the many seasonal releases, additional toppings like almond pieces, cookie crumbles, or caramel swirls are applied to the wet chocolate shell before it fully sets. These inclusions are dispensed via gravimetric feeders or rotating drum applicators that ensure even distribution. Once enrobed and topped, the bars are transferred into a secondary hardening tunnel for final crystallization. This second blast freezer brings the core temperature of the bar down to around -18 degrees Celsius or lower, locking in the texture and ensuring long-term stability. After hardening, the bars move into the packaging area, a highly automated zone designed for speed and hygiene. Here, the products are first visually inspected, sometimes with the help of AI-based vision systems, to detect any surface defects, asymmetry, or misapplied toppings. Acceptable bars are funneled into flow wrapping machines that wrap each individual bar in a high barrier plastic film. This film is not just for branding and appeal, it plays a vital role in protecting the product from moisture migration, freezer burn, and flavor loss. Each wrapper is pre-printed with product information, including batch codes, manufacturing dates, allergen warnings, and nutritional data. A thermal transfer printer applies dynamic codes as the film passes through the wrapping head. After sealing, the bars are grouped in cartons, often using robotic arm sorters, and packed into corrugated boxes, ready for cold chain logistics. Throughout the production process, quality control is embedded at every stage. Inline sensors measure everything from ice cream viscosity to chocolate temperature, while human inspectors perform taste tests and texture evaluations on random samples. Microbiological swabbing, allergen verification, and weight calibration are also conducted routinely. Any deviation triggers alarms that pause the line until the issue is resolved. This level of scrutiny is necessary, not only to maintain consistency, but to ensure compliance with international food safety standards such as HACCP, ISO 22000, or BRC Global Standard. Once boxed, the finished Magnum bars are palletized and moved into cold storage. These industrial freezers maintain a stable environment at around -25 degrees Celsius, critical for preserving the product's texture and preventing recrystallization. From there, refrigerated trucks equipped with temperature monitoring systems distribute the bars to regional depots, supermarkets, and convenience stores. The logistics chain is tightly managed to ensure the product remains frozen solid all the way to the point of sale. Interestingly, the entire Magnum production system is designed for modularity and scalability. Production lines can be quickly reconfigured to produce different flavors, bar sizes, or seasonal variants, thanks to programmable logic controllers and standardized mold sets. In larger plants, multiple lines may run in parallel, each specializing in a different SKU. Automation doesn't just improve efficiency, it reduces contamination risks and allows for extremely precise control over ingredient ratios, freezing rates, and coating thickness. What makes Magnum truly remarkable is how it bridges artisanal quality with industrial efficiency. Despite being mass-produced, each bar is designed to evoke the sensory richness of a handcrafted dessert. The sound of the chocolate snap, the creaminess of the core, and the exact melting point of the coating are all fine-tuned, using years of research in food science and process engineering. Even sustainability has entered the picture. Many Magnum facilities are now integrating closed-loop water cooling systems, solar-powered equipment, and blockchain-enabled traceability for key ingredients like vanilla and cocoa. This reflects a growing consumer demand for transparency and environmental responsibility, even in the indulgent world of frozen treats. It all begins with the foundational dairy mix, which forms the base for every pint. Ben & Jerry's ice cream is made from cream, condensed skim milk, liquid sugar, and egg yolks. These ingredients are sourced from dairy farms that are part of the Caring Dairy program, a sustainability initiative focused on animal welfare, environmental stewardship, and farmer livelihood. The cream and milk arrive at the factory in insulated tanker trucks, which are sealed and refrigerated to ensure freshness. Each delivery is tested on arrival for butterfat content, temperature, and microbial safety before being offloaded into large, refrigerated stainless steel storage tanks. Once approved, the raw ingredients are metered into blending tanks, where the liquid base is formulated. These tanks are equipped with high-shear mixers and homogenizers that ensure a uniform dispersion of fat and solids. Egg yolks are added not just for richness, but as natural emulsifiers, giving Ben & Jerry's its thick, custard-like body. Depending on the flavor being produced, this base mix may also include cocoa powder, pure vanilla extract, or natural flavorings, each added in precisely measured quantities under strict batch protocols. Every component is logged and traceable, complying with both food safety regulations and the company's transparency standards. Next, the liquid mix is pasteurized to eliminate potential pathogens. This is done through a continuous flow system, typically a plate heat exchanger, that rapidly heats the mixture to around 83 degrees Celsius for about 15 seconds. The mix is then cooled instantly to below 4 degrees Celsius and sent to aging tanks. These stainless steel tanks are fitted with slow-moving paddles to keep the mix from separating while it rests for a minimum of 4 hours and often up to 12. Aging allows the milk proteins and emulsifiers to fully hydrate, improves the texture, and helps develop the desired mouthfeel in the final product. Once the mix has aged properly, it's time for flavoring and freezing. This is one of the most tightly controlled and choreographed stages in the process. The aged base is pumped into continuous freezers, large barrel-shaped machines that scrape, whip, and chill the mix simultaneously. In these machines, the mix is cooled down to about -5 degrees Celsius and aerated with tiny amounts of air. Ben & Jerry's is known for its super premium designation, which means it contains less overrun than standard ice cream. Overrun refers to the amount of air incorporated during freezing, and low overrun results in a denser, creamier product. The target overrun for Ben & Jerry's is around 20%, far below the 80 to 100% often found in cheaper brands. As the ice cream exits the continuous freezer, it is still semi-soft and ready for the next hallmark of Ben & Jerry's, the mix-ins. The brand's chunky identity relies on adding generous portions of solid inclusions such as cookie dough, fudge brownies, peanut butter cups, and nuts. These ingredients are pre-prepared and kept frozen or chilled to prevent them from melting or breaking apart during mixing. They're delivered to the factory in bulk containers and are inspected for uniformity and contamination. Depending on the flavor, the inclusions are automatically dispensed into the flow of semi-frozen ice cream using an ingredient feeder. This is a sophisticated auger system that evenly meters chunks into the product stream without jamming or crushing them. The swirl elements, like caramel ribbons, fudge streaks, or marshmallow sauces, are added through a separate injection system. As the ice cream flows through a special section of the filler pipeline, precision nozzles inject thick sauces in continuous streams or pulses depending on the design. This ensures even distribution without blending the swirls into the base, preserving the distinct streaks of flavor that fans love. With all mix-ins and swirls incorporated, the ice cream is now ready for packaging. The semi-solid product is pumped into pre-labeled pints using automatic piston fillers. These fillers are calibrated to deposit exactly 473 milliliters of ice cream into each container with minimal air pockets or overflow. The filling heads descend onto the pint cups with synchronized timing, and sensors detect the proper fill level. The filled pints are then sealed with a foil lid and capped by a high-speed lidding machine. A light pressure press ensures that the lid sits flush, followed by a tamper-evident heat band or film seal in some plants. From here, the pints travel immediately into a hardening tunnel, an ultra-low temperature environment often referred to as a spiral freezer or blast tunnel. Operating at temperatures around -40 degrees Celsius, this tunnel freezes the pints solid in under 30 minutes, using high-velocity air circulation. Quick hardening is critical not only for texture and shelf life, but also to prevent the inclusions from sinking or rising within the pint before solidification. The spiral hardener moves the pints upward or downward along a long helical path, maximizing contact time while minimizing floor space. Once hardened, the pints are conveyed to a packaging line where they are inspected, date-coded, and boxed for shipment. Vision systems and weight sensors perform final quality checks, verifying that labels are correctly applied, seals are intact, and there are no underweight or overfilled pints. Acceptable pints are collected into cartons, which are stacked onto pallets by robotic arms. These pallets are wrapped in plastic film and stored in cold storage at -25 degrees Celsius while awaiting distribution. Distribution logistics are tightly controlled to preserve the quality of the ice cream. Temperature-controlled trucks transport the product to regional distribution centers, supermarkets, and scoop shops. Each truck is equipped with data loggers that track interior temperatures, and any deviations are flagged as potential compromise points. Even at the point of sale, Ben & Jerry's invests in branded freezers with specific temperature and airflow settings to preserve texture and flavor. While the process is highly industrialized, Ben & Jerry's maintains a close connection to its values. Fairtrade certified cocoa, vanilla, and sugar are used wherever possible. The brownie pieces come from Greyston Bakery, a New York-based social enterprise that employs people with barriers to employment. Many of the flavor developments happen in pilot-scale test kitchens, where new combinations are trialed in small batches before being scaled up. Once a new recipe is approved, the production team carefully adapts it to the factory setting, ensuring that the large-scale version retains the chunky, indulgent characteristics of the original. Clean-in-place systems are another critical component of the factory's operation. Between each production run, especially when switching flavors, the lines must be thoroughly cleaned to prevent cross-contamination. CIP systems flush the internal surfaces of mixers, freezers, pipes, and fillers with a series of hot water, caustic detergent, and sanitizing solutions. These cycles are automated and monitored by sensors to ensure complete sanitation while minimizing water and chemical usage. Factory workers and quality assurance teams play an essential role in the process. From ingredient reception to final packaging, trained personnel conduct sensory evaluations, sample testing, and equipment calibration. Every batch is logged, sampled, and stored for traceability. Flavor consistency is particularly important for a brand like Ben & Jerry's, where fans expect each pint of half-baked or cherry Garcia to taste exactly the same as their last. In recent years, automation and data analytics have further optimized the process. SCADA systems monitor real-time parameters like flow rate, temperature, and mixing speed. If a deviation occurs, alerts are sent to operators who can intervene before a quality problem arises. At the same time, this data is archived for trend analysis and continuous improvement initiatives. Despite all the technology, what sets Ben & Jerry's apart is the commitment to texture, flavor, integrity, and social values. Making a pint of ice cream that contains a half dozen different textures, swirls, and inclusions without compromising on any aspect requires not just precision, but passion. It's not merely about freezing cream and sugar, it's about orchestrating a complex ballet of ingredients, machinery, and people to produce something that brings joy in every spoonful. The process begins with the sourcing of raw ingredients, mainly fresh cream, whole milk, sugar, and egg yolks. Häagen-Dazs prides itself on using as few ingredients as possible, which means that the quality and consistency of each one is paramount. The cream and milk are typically sourced from regional dairy suppliers that meet strict quality and animal welfare standards. Upon arrival at the production facility, these dairy ingredients are pumped from insulated tanker trucks into temperature-controlled holding tanks. These tanks maintain the cream and milk at around 2 to 4 degrees Celsius to preserve freshness. Before they are cleared for use, samples from each delivery are sent to the on-site quality assurance lab for immediate testing. These tests measure fat content, microbiological safety, and protein levels to ensure the mix will deliver Häagen-Dazs's signature richness. Once the raw ingredients pass inspection, they are moved to large blending tanks equipped with high-shear mixers. These stainless steel vessels allow the controlled integration of the cream, milk, liquid sugar, and egg yolks. Egg yolks are particularly important in Häagen-Dazs formulations as they act as a natural emulsifier, helping to bind the fat and water components together into a smooth, stable emulsion. This use of real eggs is a hallmark of the brand's French-style custard base. In some flavors, pure vanilla extract or cocoa powder is added at this stage, depending on the batch being produced. Every ingredient is weighed and logged, and the entire recipe is controlled by a central PLC system that ensures each batch is blended to exact specifications. Following the blending step, the liquid mix is subjected to pasteurization. This critical food safety step involves rapidly heating the mix to about 82-85 degrees Celsius for 15 seconds using a plate heat exchanger. This kills off any potential pathogenic bacteria while preserving the functional qualities of the proteins and emulsifiers. Immediately after pasteurization, the mix is cooled to below 4 degrees Celsius and sent to aging tanks. These tanks, which are usually insulated and jacketed for precision cooling, hold the mixture for 8 to 24 hours. During this aging period, the proteins and emulsifiers fully hydrate and the fat crystals begin to form, a process that is essential to creating the dense, creamy mouthfeel that distinguishes Häagen-Dazs from other ice cream brands. Once aged, the mixture is ready to be frozen. The liquid base is pumped into continuous freezers, which are rotating barrel machines designed to freeze and aerate the ice cream simultaneously. Häagen-Dazs ice cream is notable for its low overrun, typically around 20% or less. This means that very little air is incorporated during freezing, resulting in a denser, heavier product. This contrasts with standard commercial ice cream, which may contain 100% overrun, effectively doubling the volume through air alone. The continuous freezer chills the mix to about -5 degrees Celsius while blending it with microbubbles of air to achieve the desired consistency. Once the product exits the freezer, it's in a soft serve state, thick enough to hold its shape but still pliable. At this point, any swirl ingredients, flavor pastes, or inclusions such as chocolate chunks or fruit pieces are added. Unlike brands that pack their products with multiple layers of mix-ins, Häagen-Dazs tends to focus on refined and restrained combinations. However, for flavors like chocolate chip or dulce de leche, ingredient feeders are used to incorporate solid components without damaging them or disrupting the flow of the product. These feeders use auger screws and synchronized timing to introduce the chunks or ribbons directly into the stream of semi-frozen ice cream, ensuring even distribution. After inclusions are added, the ice cream flows to the filling station. Pints, which are pre-labeled and stacked in a hopper, are automatically placed onto a conveyor system that moves them beneath piston fillers. These fillers are designed to deposit exactly 14 fluid ounces of product into each container. The fill process is timed perfectly to prevent splashing or overfilling, and sensors monitor the weight and height of each pint as it passes. After the pint is filled, a foil seal may be applied to help maintain freshness and reduce freezer burn. Then, the lid is placed using a robotic arm and lightly pressed for an airtight fit. From here, the pints are conveyed into a spiral hardening tunnel, a vertical, corkscrew-shaped blast freezer that rapidly brings the core temperature of each pint down to below -20 degrees Celsius. This freezing must occur quickly to prevent the formation of large ice crystals, which would ruin the smooth, dense texture. The spiral design maximizes surface area and airflow while minimizing the footprint on the factory floor. Depending on production volume and configuration, the tunnel can hold hundreds of pints at a time, moving them slowly along the spiral track for 30 to 60 minutes. Once hardened, the pints exit the tunnel and move into the packaging zone. Each pint is inspected for proper sealing, correct labeling, and visual defects. This inspection process may include optical scanners and machine vision systems that check for off-coloration, misaligned labels, or foreign material. Some facilities also use X-ray systems to detect any hard contaminants that may have entered during the filling process, particularly in flavors with inclusions like nuts or toffee. After passing inspection, the pints are grouped and boxed into secondary packaging, usually corrugated cardboard cases containing 6 or 8 units. These boxes are sealed and barcoded for traceability, then stacked onto pallets by an automated robotic palletizer. Each pallet is wrapped in shrink film to stabilize it for cold storage. The wrapped pallets are moved to a deep freeze warehouse area kept at -25 degrees Celsius, where they await transportation. Distribution of Häagen-Dazs products follows a tightly regulated cold chain protocol. Reefer trucks, equipped with real-time temperature tracking, pick up pallets and deliver them to regional warehouses or retail outlets. Any temperature breach in the chain is recorded and flagged, as a product exposed to temperatures above -12 degrees Celsius for prolonged periods risks partial thawing and textural damage. The robust cold chain logistics ensure that every pint maintains the same texture and quality, whether it's eaten in Paris, Tokyo, or New York. Throughout this entire process, food safety and quality assurance teams are deeply involved. Every step, from ingredient reception to final shipping, is documented under a comprehensive HACCP plan. Daily samples are taken from every production run and stored for shelf life testing. Sensory panels evaluate texture, flavor, aroma, and meltdown properties. Microbiological testing is conducted regularly to verify sanitation effectiveness. In the event of any deviation from standards, production can be halted and equipment cleaned using automated clean-in-place systems. Häagen-Dazs also invests in sustainable practices wherever possible. Many of their dairy farms operate under environmentally conscious guidelines, and the brand continues to explore renewable energy options for its manufacturing facilities. Water use, waste generation, and energy consumption are tracked and reported as part of the company's larger environmental footprint goals. What's remarkable about Häagen-Dazs' production process is how it maintains artisanal quality while operating at global scale. Every pint is the result of a finely tuned interplay between ingredients, equipment, and process control. The use of real eggs and cream, the low overrun, the gentle treatment of inclusions, and the quick freezing spiral tunnel all contribute to a final product that feels indulgent and rich with every bite. And while machines do much of the heavy lifting, people remain at the heart of the operation, checking batches, tasting new formulations, maintaining equipment, and ensuring that every pint lives up to the brand's heritage. In an age where so much food is optimized for speed and cost, Häagen-Dazs stands out by elevating the basics. It doesn't chase novelty for novelty's sake. Instead, it doubles down on purity, richness, and consistency, transforming simple ingredients into something decadent through a meticulously managed production process.